Good evening, weary traveler of thought. Welcome, as we prepare to drift into the quiet depths of the cosmos, to explore the profound questions that stir the very fabric of reality, gently guiding us towards slumber. Tonight, we embark on a journey, not merely through a dusty catalog of scientific facts or abstract equations, but through the very tapestry of human thought that has woven our understanding of existence itself. You see, our most intricate and expansive knowledge of time, that elusive current upon which all our lives drift, and of space, that silent, boundless stage upon which all unfolds, owes its deepest insights, its most revolutionary breakthroughs, not primarily to the contemplative musings of professional philosophers. While their intellectual inquiries are invaluable, the true architects of our modern cosmic understanding have been, far more often, the patient, persistent, and often painstaking laborers of mathematicians and physicists. These are the tireless artisans of the universe, who, armed with the precise tools of logic, rigorous observation, and daring theoretical abstraction, have dared to probe the very structure of the cosmos, irrevocably reshaping our most cherished, often subconscious intuitions about the nature of existence, about where we truly stand in this grand, unfolding drama. So, settle in, let your thoughts gently unfurl as we delve into these ancient and modern mysteries. For uncounted millennia, stretching back through the mists of history from the philosophical awakenings of the heroic age of Greece, a time of bold inquiries into the fundamental nature of being and non-being, of the void and the plenum, right through to the scientific ferment at the dawn of the modern era, humanity grappled with two distinct, often conflicting visions of space. Each of these captivating concepts, in its own way, vied for intellectual dominion within the human mind, shaping how people conceived of their world and the cosmos beyond. These were the enduring ideas of dressed space and undressed space. Now, undressed space, the abstract concept of a pure void, an emptiness existing entirely independently, a sheer, unblemished nothingness, was, for the ancient intellect, initially a lofty and often unsettling abstraction. It was difficult, profoundly challenging, for many to truly grasp, for how, the mind pondered, could absolute nothingness be? How could it possess existence, let alone properties or dimensions? The very idea felt paradoxical, a contradiction in terms, almost a philosophical affront. Could you imagine a place where literally nothing resided? Far more intuitive, more readily embraced by human perception, and perhaps more comforting to the human psyche, was the idea of space as dressed. To be dressed meant to be made real, to be given tangible substance, to be rendered comprehensible by a continuous, all-encompassing covering of material or ethereal substances. This was the vision of a plenum, a cosmos where every conceivable crevice, every infinitesimal gap was filled. It was a universe where there was no room for the terrifying, almost anarchic concept of an absolute vacuum. It was a universe packed solid, a cosmic tapestry woven without a single missing thread, leaving no empty space for matter to move through effortlessly, no void for silent contemplation. Among the most influential and eloquent champions of this dressed space philosophy was the towering figure of Aristotle, whose wisdom shaped Western thought for nearly 2 millennia. With his profound conviction, he dismissed the very idea of a vacuum as a logical absurdity, an unreality that simply could not exist within the rational and interconnected order of the cosmos. For Aristotle, the concept of motion itself intrinsically required a medium, a substance against which to push or through which to travel. a fundamental premise that utterly precluded the existence of any empty void. His reasoning was elegant. If a void existed, motion within it would be unhindered, allowing for infinite speed, which he considered a logical impossibility. A feather and a cannonball, he argued, would fall at the same speed in a vacuum, a thought experiment he dismissed as absurd. This profound conviction, this absolute denial of emptiness, formed the bedrock of his geocentric cosmology, underpinning his grand vision of a finite, Earth-centered universe. In this majestic, yet contained, design, the celestial realm was comprised of a pure, immutable ether, that illustrious fifth element, perfect, unchanging, and transparent. This ether, he reasoned, ended abruptly and definitively at the crystalline sphere of fixed stars, the outermost boundary of his cosmic order. Beyond this celestial demarcation, devoid of the all-pervading ether, there could, by his logic, be no space at all, for space itself was intimately tied to the presence and properties of matter. It was a cosmos contained, a beautifully ordered universe with definite edges, a snug and comprehensible fit for humanity and its place within it. Centuries later, as medieval scholars absorbed and reinterpreted Aristotelian thought through the lens of emerging monotheistic religions, particularly Christianity, Judaism, and Islam, they found themselves confronting the theological and philosophical implications of a bounded cosmos. How, they pondered, could an infinitely powerful, omnipresent, and truly infinite God exist within a finite, material space, limited by the sphere of fixed stars? The answer, both ingenious and deeply spiritual, was to find a way to conceptually extend this dressed space, not with more matter, but by inhabiting the regions beyond Aristotle's sphere of fixed stars, with the omnipresent divine essence, with God himself. Thus, infinite space was accommodated, without recourse to the heretical or philosophically problematic notion of an Aristotelian vacuum. The universe, though conceptually finite in material extent according to the ancients, became infinitely vast through divine presence, allowing for God's omnipresence without violating the physical theories of the day. The brilliant French philosopher and mathematician René Descartes in the 17th century likewise conceived of space as indefinitely extended, but he achieved this not through emptiness, nor solely through divine presence. His solution was resolutely materialistic and mechanistic. He envisioned space as being entirely suffused with a plenum of continuous, subtle matter, an intricate, imperceptible fluid that filled every conceivable gap, leaving no atom of empty space. For Descartes, extension was matter, and therefore, wherever there was space, there must be matter. He vehemently denied the existence of any void, even the smallest one, asserting that the universe was a giant, intricate clockwork mechanism, operating through the ceaseless motion of contiguous particles in great vortices, those swirling eddies of subtle matter, leaving no empty cogs or gears. This elegant system sought to explain all physical phenomena, from planetary orbits to magnetism, through the continuous push and pull of this subtle matter, a grand, intricate, and perfectly mechanical cosmic machine. Yet, as the 17th century progressed, a profound intellectual shift began to unfold, spurred not by philosophical debate alone, but by the relentless march of empirical science, by the direct, systematic interrogation of nature itself through experimentation. A series of groundbreaking experiments, particularly those involving newly invented air pumps, most famously and dramatically demonstrated by the German scientist and inventor Otto von Guericke, with his iconic Magdeburg hemispheres, began to offer compelling, visceral proof of the existence of a vacuum. Guericke's public spectacles, where teams of horses strained unsuccessfully to pull apart evacuated copper spheres, provided undeniable, awe-inspiring evidence of the immense power of an induced vacuum, of the pressure of the surrounding air bearing down upon an empty space. These experiments convinced many, especially the emerging school of thought that would coalesce around the towering figure of Isaac Newton, that space could indeed exist without a material covering, that it could be an emptiness in its own right, a container without contents. This ushered in the revolutionary idea of Newton's absolute space. A vast, unchanging, utterly empty arena, a fixed, invisible grid against which all motion could be precisely measured, existing independently of the matter it contained. But even with this new and radical understanding of a potentially empty space, a persistent and deeply vexing challenge remained, a shadow hanging over the nascent science of optics. If space was truly empty, a void, how then could light waves, known to propagate across astronomical distances with astonishing speed, possibly traverse such a vacuum? Waves, after all, fundamentally require a medium to undulate through, a substance to carry their vibrations. Sound waves need air or water. Ocean waves need water. What did light waves need, if not the now discredited ether of Aristotle and Descartes? This fundamental conundrum, this seemingly irresolvable paradox of light's propagation through emptiness, led to the widespread postulation of a subtle, all-pervading luminiferous ether. This hypothetical, invisible, undetectable medium was believed to fill the entire cosmos, permeating even the interstellar and intergalactic voids, a kind of cosmic jelly. This mysterious substance was envisioned as the universal carrier of light, allowing light waves to undulate and propagate through its immense expanse, much like ripples across a cosmic pond. It was thought to be incredibly rigid and elastic to support light's immense speed, yet simultaneously entirely frictionless and transparent, allowing planets to orbit unimpeded and stars to shine unhindered. This concept, though ultimately flawed, provided a temporary, albeit unsatisfying, resolution to the paradox, a final clinging stubbornly to the old, dressed space intuition, even in the face of a newly acknowledged vacuum. Then, as the Grand Curtain rose on the 20th century, it brought with it a torrent of radical new ideas, a conceptual avalanche that would forever alter our perception of reality, shattering old certainties. Foremost among these intellectual seismic shifts was Albert Einstein's theory of special relativity, unveiled in its breathtaking simplicity and audacity in 1905. This revolutionary framework, born from the simple yet profound postulate that the speed of light is a universal constant for all observers, regardless of their own motion, irrevocably shattered the deeply entrenched need for a luminiferous ether. The ether, that omnipresent invisible medium, became an unnecessary, cumbersome concept, swept away by a single, elegant stroke of genius. Special relativity revealed space not as a mere emptiness, a passive container, nor as a medium, but as a dynamic, intricate physical structure, inextricably interwoven with time into a unified, four-dimensional fabric. The Cartesian idea of space as an infinitely extensible property of matter, then later Newton's conception of space as an independent, absolute continuum, a fixed, unyielding stage upon which the cosmic drama played out, both gave way. Now, with Einstein, space itself, fundamentally fused with time, became the dynamic actor, the pliable, responsive participant in the grand ballet of existence, forming what we now understand as Einstein's spacetime. It was a monumental shift in perspective, transforming the very stage into a living, responsive player in the cosmic drama, a fundamental reimagining of reality. This profound revolution in understanding, naturally and inevitably, began to reflect itself in the very language of mathematics, that universal tongue of the physical sciences, the precise articulation of cosmic truth. Centuries earlier, René Descartes had already initiated a transformative fusion of geometry and algebra, providing humanity with the indispensable tool of coordinate systems. In these systems, points in the familiar three-dimensional space could be precisely defined by a trio of numerical values, x, y, and z. The distance between any two such points was then elegantly given by the ancient and simple Pythagorean rule, a mathematical harmony extended from 2 to 3 dimensions. This algebraic framework, with its metric equations and metric coefficients, mathematical constructs that describe the intrinsic distance between points, the very measure of spatial separation, would become not just useful, but absolutely crucial for describing a universe far more complex, more nuanced, and more dynamically alive than even the most brilliant minds of Newton's era could possibly have imagined. It laid the groundwork for mapping not just flat, but curved and dynamic realities, preparing the stage for a new geometric understanding of gravity itself, a universe where the rules of geometry were no longer rigid but could bend and flex. And so, my dear listeners, we shift our focus, our quiet gaze now resting upon time itself, that most ubiquitous yet most enigmatic of phenomena. It is the relentless current upon which all our lives drift, the measure of change, the very rhythm of existence, and yet, when truly scrutinized, it eludes our grasp like a whisper in the wind, like water held in a cupped hand. Saint Augustine, the great philosopher of the 5th century, eloquently encapsulated our collective human perplexity with his poignant words that resonate deeply even today, a testament to time's enduring mystery. What, then, is time? If no one asks me, I know what it is. If I wish to explain what it is to him who asks me, I do not know. His ancient sentiment mirrors our perennial struggle, even in this age of scientific marvels, to truly grasp the core nature of this ceaseless flow. We experience time intimately, subjectively, through the ceaseless flux of our conscious experience, through the irreversible sequence of moments that define our memories and expectations, our hopes and regrets. Yet, when we attempt to define it objectively, to pin down its essence with precision, to measure it, to quantify it, it often retreats into the shadows of incomprehensibility, a ghost that refuses to be caged. Science, in its relentless pursuit of understanding, seeks to refine our raw, experiential time. It transforms it into a continuous, one-dimensional spatial dimension within its mathematical models, a rigorously defined construct amenable to analysis, prediction, and the elegant equations of physics. Yet, this powerful scientific construct, while enabling immense understanding of physical processes, often feels distant from the subjective, personal flow of our lived duration, that fleeting present moment that seems to constantly slip away, a phantom of our perception. It was in the late 19th century that Charles Hinton, a somewhat overlooked but profoundly imaginative British thinker and mathematician, initiated a truly radical revolution in our understanding of time. He dared to conceive of time not merely as a progression of moments, a ticking clock, but as a physical fourth dimension, a spatialized dimension co-equal with the familiar three spatial dimensions of length, width, and height. This bold conceptual leap gave rise to the notion of the quote-quote block universe, a profound and often unsettling philosophical concept sometimes referred to as eternalism, or four-dimensionalism. In this grand, static framework, the entire history of the universe, all events, past, present, and future, are not sequential in the way we experience them, but are laid out together, simultaneously existing, like frames on a cosmic film reel that can be viewed from any angle. Imagine a vast, four-dimensional sculpture where every moment, every event, from the first flicker of existence to its ultimate end, is already inscribed. Nothing truly changes or moves within this block universe in the way we usually understand it, for time itself is one of its dimensions, an inherent part of its fixed, immutable structure, and therefore it cannot be traversed or retraversed as if it were an external river. Our perception of movement and change, then, becomes a kind of illusion, a consequence of our consciousness, our spotlight of awareness, or our now point, traversing this fixed, unchanging reality, creating the experience of flow. This concept, though initially unsettling to our everyday intuition and sense of free will, offered a powerful, static representation of a world that appears, to our limited perception, to be restlessly dynamic. It implies a kind of cosmic predetermination, where all of history, from the first flicker of existence to its ultimate end, already exists in a timeless, four-dimensional expanse, much like a book whose pages are all written, even if you are only reading one page at a time. Yet this elegant, static block universe view invariably clashes, sometimes jarringly, with our most fundamental, visceral, and undeniable experience of time's inherent directionality, its unmistakable arrow. While many of the fundamental laws governing the microscopic world of particles, the very building blocks of reality, the dances of quarks and leptons, the interactions of photons, are remarkably time-reversible, meaning they work equally well forwards or backwards in time without violating the laws of physics. A film of subatomic collision looks equally valid played in reverse, mathematically speaking. The macroscopic world, the world of our everyday experience, is unequivocally a dropped glass shatters, its fragments scattering across the floor, entropy increasing. It never spontaneously reassembles itself into a whole glass. A human being ages, their body undergoing irreversible changes, cells decaying. They never grow younger. The branch of physics known as thermodynamics, and particularly its profound second law, dictates an immutable cosmic truth, a deep asymmetry in time. That entropy, a measure of disorder, randomness, or the amount of energy unavailable for useful work, always increases in isolated systems. Heat flows spontaneously from hot to cold, diffusing, spreading out, striving for equilibrium. It never, without external intervention, spontaneously reverses its flow, concentrating itself back to a hotspot. This aggregate, collective behavior of myriad particles, though each individual particle's interaction might be time-reversible, imposes an irreversible cosmic arrow, an undeniable march, that makes the future distinctly different from the past. A comforting mug of coffee cools inevitably, its heat dissipating into the room. Mighty stars exhaust their nuclear fuel and die, their ordered structure yielding to diffuse remnants of gas and dust. And universal order, without constant input of energy, tends inexorably towards disorder, towards a state of maximum entropy. It is the vast, cumulative effect, the emergent property of billions upon billions of individual, time-reversible interactions, much like individual brushstrokes, when viewed from a distance, coalesce to reveal a complete, irreversible painting that defines time's inexorable flow, creating the arrow of time, rather than the isolated, time-reversible dance of any single particle. This macroscopic arrow of time is what truly differentiates our lived experience from the static tapestry of the block universe, giving us a sense of past and future, This undeniable directionality and the feeling of motion bring us inevitably to the elusive now, that fleeting, vivid, and intensely personal segment of time we constantly inhabit, that razor's edge between the past and the future. We often intuitively envision time as a river, its currents carrying us along, with our now drifting through it, the future inexorably approaching from upstream, and the past receding endlessly downstream into memory, into the unchanging annals of history. But the moment we pose the seemingly simple question, at what speed does this now move through the river of time, we are immediately confronted with a bewildering, almost recursive paradox. This quickly reveals the intricate trap of serial time, a regression of times within times, an infinite sequence of meta-times, each measuring the flow of the one below it. If time is fully spatialized, if it is merely another dimension like height or width, as in the block universe concept, how then can there be genuine movement through time? A movement, after all, requires a change in position over some temporal duration. If that duration is itself time, then what measures its flow? The question becomes circular, a conceptual loop without resolution, a recursive riddle. This apparent transience of existence, this feeling of constant becoming, of being carried forward into the unknown, remains a profound mystery, one that perhaps defies purely physical explanation. It may well be a non-physical peculiarity of consciousness itself, a subjective illusion born from the very act of experiencing, rather than an objective, measurable feature of the cosmic clockwork, a trick of our minds within a static reality. And speaking of paradoxes and the popular imagination, the very notion of time travel, so ardently beloved and endlessly explored in the realms of science fiction, frequently rests upon a fundamental misunderstanding of the nature of spacetime itself, as described by modern physics. Physical travel into the past, as depicted in countless narratives of altering history or meeting one's younger self, is not impossible merely for technological reasons, for lack of a powerful enough machine, a sufficiently advanced temporal drive. Rather, it is fundamentally impossible because it violates the deep, immutable nature of world lines in space-time. Our universe's spacetime, once formed and evolved, is a fixed and unchangeable reality. It is a complete and unalterable record of all events, a four-dimensional block. Nothing physical can simply vanish from one point on its pre-existing world line and magically reappear at an earlier or later point, altering its past. To do so would imply erasing or rewriting a segment of reality that has already unfolded and is an inherent part of the fixed continuum. What H.G. Wells, in his seminal work The Time Machine, envisioned with his temporal conveyance was, at best, a metaphysical travel along an existing world line, a change in perspective or experience for the traveler, perhaps a way to view the past rather than an alteration of the very fabric of space-time itself. The past is not a place we can revisit and alter. It is an inherent, unchangeable part of the four-dimensional whole, existing as much as the present or future. The ancient Greek philosophers, in their profound inquiries, truly laid the groundwork for many of these timeless debates. They grappled with these same dual aspects of reality that continue to challenge and tantalize us today. Parmenides, on one hand, famously emphasized static, unchanging being, the eternal, unified, immutable reality that underlies all appearances, arguing that change was an illusion. On the other, Heraclitus passionately championed dynamic, ceaseless becoming, the constant flux and change that defines existence, famously stating that one cannot step into the same river twice, for both the river and the person have changed. He saw reality as a constant flow, a fire. Zeno's paradoxes, such as the famous Achilles and the tortoise or the flying arrow, were designed precisely to highlight the inherent logical problems and apparent contradictions that arise when we try to conceptualize continuous motion and the division of time and space into infinite smaller parts, showing how our intuition can betray us. These ancient dilemmas echoed across civilizations and centuries, challenging fundamental assumptions about motion and duration. The Arab theologians of the Kalam school in the 10th century proposed a truly unique and radical solution to the problem of transience and continuous motion: atomic time. They posited that time was not continuous, but rather comprised of indivisible, discrete instants of being, moments that were constantly recreated anew by a divine will. Each moment was a fresh creation, offering a fascinating resolution to the paradox of transience, suggesting that the universe was not intrinsically changing but was being perpetually remade, moment by moment, by an active creator. Perhaps, in some future more complete theory of quantum gravity, one that harmonizes the discrete and the continuous, the conjugate aspects of static being and dynamic becoming, will finally be reconciled within a grander unified framework, fundamentally altering not just our understanding of time, but with it, the entire edifice of cosmology itself, offering a new lens through which to perceive the universe's ultimate, unfolding nature. Such a theory would truly bridge the ancient philosophical divide. As our minds continue to settle into the cosmic rhythm, let us shift our attention from the enigma of time to the surprising, flexible nature of space itself. For uncounted millennia, the elegant and seemingly unassailable system of Euclidean geometry, meticulously codified by Euclid in his monumental work, The Elements, around the 3rd century BC, reigned supreme as the undisputed truth of spatial reality. Its 5 axioms, those foundational, self-evident truths upon which its entire structure was built, seemed to describe the world with perfect fidelity, reflecting the clear logic of our senses and our everyday experience. Among these axioms, the parallel postulate, which states that through a point not on a given line, only one line can be drawn parallel to the given line, appeared intuitively obvious, an inevitable necessity of thought, as the great philosopher Immanuel Kant famously believed. It felt like an inherent feature of rational perception, a truth woven into the very fabric of how we apprehend space, beyond all doubt, a universal and unchangeable truth. Yet, despite its compelling self-evidence, this intuitive truth remained stubbornly unproven from the other 4 axioms, a persistent mathematical itch that generations of mathematicians tried for centuries to scratch, seeing it as an irritating imperfection in an otherwise perfect system. Countless hours were spent attempting to derive it from the other 4, all in vain, leading only to deeper frustration. It was not until the 19th century that a group of audacious and brilliant mathematicians, true intellectual rebels, figures like Carl Friedrich Gauss, Nikolai Lobachevsky, János Bolyai, and later the visionary Bernhard Riemann, dared to challenge this ancient dogma, to question the very necessity of thought that Kant had proclaimed. They conceived of and rigorously constructed entirely new, non-Euclidean geometries, where the parallel postulate simply did not hold true. These revolutionary alternative spaces, known as hyperbolic and spherical geometries, were, like Euclidean space, uniform, meaning they were homogeneous, appearing the same everywhere, and isotropic, appearing the same in all directions on sufficiently large scales. Yet, crucially, unlike Euclidean space, which possesses no intrinsic scale, these new spaces possessed an inherent, measurable scale, a characteristic length or radius denoted by r. This intrinsic scale meant that their properties changed depending on the scale at which you observed them. The consequences of these new geometries were astonishing, even mind-bending, and thoroughly counterintuitive to our everyday experience. In hyperbolic space, for instance, a space often visualized as a saddle shape. Through a point not on a given line, many lines can be drawn that are parallel to the given line, fanning out into an infinite array of diverging paths. Moreover, in such a space, the familiar laws of proportionality are altered. The circumference of a circle is greater than the familiar pi times its diameter, 2 pi r, as if the space were pulling it outward. Conversely, in spherical space, a geometry of positive curvature, like the surface of a globe, no parallels to a given line exist, as all straight lines, which are great circles, like the equator, or lines of longitude, eventually intersect if extended far enough, even if they started parallel. And here, a circle's circumference is, perhaps surprisingly, less than pi times its diameter, as if the space were pulling it inward. Perhaps the most accessible manifestation of these new geometries, and indeed the one used to detect curvature from within the space, lies in the sum of a triangle's angles. In Euclidean space, this sum is always precisely 180 degrees, but in hyperbolic space, the sum is less than 180 degrees, while in spherical space it is greater. These deviations are subtle for small triangles, barely noticeable, but become dramatically pronounced as the triangles grow larger, encompassing more of the space's intrinsic curvature, revealing the true nature of its geometry. To help us grasp these profoundly abstract concepts, we often consider curved two-dimensional surfaces embedded in a higher dimension, such as the familiar surface of a sphere, which possesses uniform positive curvature, or the undulating surface of a saddle, which exhibits uniform negative curvature. A sphere's surface, like that of our Earth, is finite in area yet completely unbounded. One can travel across it endlessly in any direction without ever encountering an edge. Its straight lines, the shortest paths between 2 points, are great circles, like the equator or lines of longitude, and any two such straight lines drawn on its surface will always intersect, demonstrating its positive curvature. A saddle, by vivid contrast, demonstrates negative curvature, a form of open space where straight lines diverge rapidly, much like two initially parallel paths on a mountain pass will eventually spread far apart. But it is crucial to understand that curvature is not merely an extrinsic property, something observed only from outside the space by a higher dimensional being. It is an intrinsic property of space itself, measurable by inhabitants within that space, without any need for a higher dimensional embedding. For example, by carefully summing the angles in very large triangles drawn across their space, or by observing how vectors change their orientation when parallel transported, moved without rotation keeping the same relative direction, around closed loops, the local curvature can be precisely determined from within. Georg Riemann, building upon Gauss's foundational work, extended this genius, generalizing the concept of intrinsic curvature to 3, 4, and even higher dimensions, creating a sophisticated mathematical framework for analyzing arbitrary curved manifolds. He envisioned space not as a rigid, passive stage, but as a flexible, dynamic participant in the cosmic drama, capable of bending and warping, twisting and stretching. His powerful mathematical invention, the Riemann curvature tensor, a complex mathematical object describing the curvature at every point in space, would become absolutely central to Einstein's later vision of gravity. Indeed, William Clifford, a brilliant young English mathematician with astonishing prescience, famously dreamt of this very future decades before Einstein, prophetically proposing that variations in space's curvature were what truly constituted the motion of matter, a profound, almost magical anticipation of the core idea of general relativity, a foresight that echoed through the coming scientific revolution, linking geometry and physics in a way no one had quite imagined. As we gently drift deeper into the night, let us carry these ideas of flexible geometry with us, for they are the keys to unlocking the next great cosmic revelation. For centuries, Isaac Newton's majestic universe had provided a comfortable, absolute framework for understanding the cosmos. It posited an absolute space, a fixed and unchanging arena, an invisible, unmoving grid against which all motion could be precisely measured. A cosmic stage that was always there, unmoving. And alongside it, an absolute time, a universal clock ticking uniformly for all observers, everywhere, independent of their location or motion. This intuitive framework, so deeply embedded in our everyday experience, was the bedrock of classical physics, a system that successfully explained everything from falling apples to orbiting planets with breathtaking accuracy. But the late 19th century brought a seismic shift, a profound crack in this elegant edifice of absolute truth, a whisper of something more profound. The pivotal Michelson-Morley experiment, performed in 1887, was meticulously designed to detect the Earth's motion through the hypothetical luminiferous ether, that supposed universal medium for light waves. Its stunning, utterly unexpected result, that the speed of light c was found to be constant for all observers, regardless of their own motion or the motion of the source of light, sent shockwaves through the scientific community. It unequivocally shattered not only the ether theory, rendering that cosmic medium utterly superfluous and experimentally undetectable, but also the cherished centuries-old notion of absolute space and time. It suggested something fundamentally deeper, more counterintuitive, was at play, demanding a complete reevaluation of our most basic assumptions about reality. It was into this intellectual void, this crisis of classical physics, that Albert Einstein, in his miraculous year of 1905, stepped with his revolutionary theory of special relativity. With breathtaking simplicity and audacious insight, he postulated two fundamental principles. First, that the laws of physics are the same for all observers in uniform, unaccelerated motion. This is the principle of relativity. And second, and perhaps even more radical, that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these two deceptively simple postulates, he derived truly astonishing consequences that defied common sense but were mathematically rigorous and experimentally verifiable. Ultimately, he fused space and time, those previously distinct and independent entities, into a single, indivisible, four-dimensional space-time continuum. No longer could they be considered separate backdrops for events. They were inextricably linked, two facets of the same underlying dynamic reality. In the elegant new geometry of special relativity, individual intervals of space and time are no longer absolute quantities that everyone agrees upon. Instead, they are found to be relative, meaning their measured values, lengths and durations, depend profoundly on the observer's state of motion. What one observer measures as a certain duration of time, another moving relative to them will measure as a different, either longer or shorter duration. Similarly for spatial distances, which can appear contracted in the direction of motion. This phenomenon is vividly demonstrated by time dilation, where moving clocks tick slower relative to stationary ones, and length contraction, where moving objects appear shorter in their direction of motion. These are not illusions, but real physical effects. But amidst this bewildering dance of relativity, where individual measurements of space and time depend on your perspective, two profound invariants emerge, unyielding constants upon which all observers, regardless of their relative motion, can absolutely agree. The first, as hinted by the Michelson-Morley experiment, is the speed of light c, which remains constant for everyone, everywhere, an ultimate cosmic speed limit, and a fundamental constant of the universe, the same for all. The second, and perhaps even more conceptually profound, is the spacetime interval. This invariant quantity, often calculated as time interval squared, space interval squared, that crucial distinctive minus sign in the mathematical formula, which gives spacetime its unique non-Euclidean Minkowski geometry, a geometry far different from the intuitive Euclidean space, is the true measure of separation between two events in spacetime, a value that all observers, no matter how they are moving, will universally agree upon. This is a testament to the underlying unity, consistency, and absolute nature of spacetime itself, a deeper reality beneath the relative appearances. As Hermann Minkowski, Einstein's former mathematics professor, famously and poetically declared in 1908, giving a powerful and prophetic voice to this new reality. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. His words eloquently captured the essence of the revolution. A new, more fundamental entity, spacetime, had been discovered, a single, interwoven fabric of existence. The very geometry of spacetime, dictated by that unique minus sign in the spacetime interval equation, leads to astonishing and often deeply counterintuitive consequences that challenge our everyday Euclidean perceptions of distance and time. In ordinary, flat, three-dimensional space, the shortest distance between 2 points is, of course, a straight line. But in the four-dimensional tapestry of spacetime, the situation is profoundly inverted. The longest path, as measured by the elapsed proper time, the spacetime interval experienced by an observer moving along that path, between two events is actually a straight world line, a path of unaccelerated, inertial motion. Any deviation from this straight path, any acceleration, will result in less elapsed proper time. This profound distinction is the essence of the famous twin paradox, which, despite its misleading name, is not a paradox, but a confirmed physical reality, a direct consequence of special relativity. Imagine two identical twins. One remains on Earth, experiencing the relatively straighter world line of near-inertial motion through spacetime. The other embarks on an arduous journey at an incredibly high relativistic speed, undertaking powerful accelerations and decelerations to depart from Earth and then return. This journey causes the traveling twin to follow a bent, non-inertial world line through spacetime, a path that deviates from the straightest possible path. Upon their reunion, the twin who embarked on the relativistic journey will have experienced less elapsed time. They will have aged less than their stay-at-home sibling. Their relative motion, and specifically the acceleration experienced by the traveling twin during departure and return, causes their personal clocks, their very biological processes, to tick at different rates, resulting in an asymmetrical aging effect. This remarkable phenomenon is not merely theoretical. It has been beautifully and repeatedly confirmed by precision experiments, most notably with high-energy particles like muons. These unstable subatomic particles, when accelerated to relativistic speeds in particle accelerators, are observed to decay more slowly, their dilated lifetimes a direct, undeniable testament to the reality of time dilation, a cornerstone of special relativity. Special relativity, while revolutionizing our understanding of space and time and their intertwining, also illuminates another crucial aspect of the cosmos. While velocities are relative, meaning they depend on the observer's frame of reference, accelerations remain absolute. An observer undergoing acceleration can always feel the forces acting upon them: the push of a rocket, the pull in a turning car, the force of gravity, distinguishing their state from an inertial, unaccelerated one. This absolute nature of acceleration was a key insight that Einstein carried forward. The laws of physics themselves, as described by special relativity, are covariant, meaning they take the identical mathematical form for all observers moving at constant uniform velocity relative to one another. This principle ensures the consistency and universality of physics across all inertial frames. However, special relativity, profound as it was only the first act in Einstein's cosmic drama. It masterfully described the universe of uniform motion, but it awaited an even grander theory, a more encompassing framework, to unify gravity, that pervasive, mysterious, and still unexplained force, with this radical new understanding of spacetime, and to finally account for the universal experience of acceleration, the feeling of weight, tying it all into the very geometry of the cosmos. As we journey further into the profound landscape of modern physics, we arrive at the culmination of Einstein's genius, a theory that transformed gravity from a force into a fundamental property of the universe's very structure. The profound intellectual leap from Isaac Newton's elegant, clockwork celestial mechanics to Albert Einstein's sweeping cosmic dance represents one of the most remarkable conceptual revolutions in human history, a complete reimagining of reality itself. This journey begins with a seemingly simple, yet deeply revelatory insight, one that bridges the gap between acceleration and gravity, forever linking them, the, quote, principle of equivalence. This foundational principle asserts that, locally, within any small enough region of spacetime, gravitational forces and inertial forces are fundamentally indistinguishable. Let us immerse ourselves in a thought experiment, a classic scenario that vividly illuminates this profound truth. Imagine, if you will, a small, perfectly sealed, windowless laboratory, a self-contained box, adrift in the vast, empty reaches of space, far removed from the gravitational influence of any stars, planets, or other massive bodies. This laboratory is moving freely, unaccelerated, in what we define as an inertial state. Any experiment performed inside, a dropped ball, a pendulum swinging, a light beam traversing the room, would reveal no internal forces acting upon objects. They would simply float, weightless, in unchanging trajectories, perfectly still or moving uniformly. Now let us imagine that same laboratory in a different scenario, falling freely, perhaps, towards the surface of a massive star, or indeed towards the Earth, with its engines off. As it plunges through the gravitational field, accelerating ever faster due to gravity, the gravitational pull of the star or planet is precisely, perfectly cancelled by the inertial force arising from the lab's acceleration, creating an effective state of weightlessness. The experimenters inside would still detect no net force. The dropped ball would still float weightlessly relative to the floor. From their perspective within the sealed box, they would again conclude they are in an inertial state, even though they are profoundly accelerating in relation to the larger gravitational body. Conversely, consider a laboratory resting on the Earth's surface, experiencing the familiar, constant pull of gravity, objects pressing down on the floor. Compare this to a rocket-accelerated laboratory in the deep void of space, far from any celestial bodies, its engines firing continuously, constantly pushing it forward. To the occupants of the accelerating rocket, objects would press against the floor with a weight that is, from their local perspective, entirely indistinguishable from the force of gravity. Locally, without any external reference points, these two scenarios, The feeling of gravity and the feeling of being accelerated are identical in their observed effects. This principle, articulated in its strong form by Einstein, suggests that the laws of physics, including special relativity itself, must hold true even in free-falling and thus locally accelerated systems, blurring the lines between gravity and acceleration in a profound and fundamental way, making acceleration the key. This led directly to a second, even more revelatory insight, a realization that forever linked the universe's geometry with its most pervasive force. That geometry and gravity are not merely related, but are intimately, inextricably intertwined, two sides of the same cosmic coin, a single, unified phenomenon. Let us once again use a visualization to grasp this profound concept. Picture a large, tautly stretched rubber sheet, perfectly flat and unperturbed in the absence of any mass or energy. Now, imagine rolling a small ball bearing across its surface. It follows a perfectly straight path, as dictated by Euclidean geometry, unimpeded. But now, introduce a heavy bowling ball onto the center of that rubber sheet. Its weight creates a visible depression, a profound curvature in the fabric of the sheet. This curvature, this geometric distortion of the sheet's surface, serves as a powerful analogy for gravity. Now roll the small ball bearing nearby, initially aiming for a straight trajectory. Instead of continuing in a straight line, its path will be deflected, bending inward, following a curved trajectory around the heavy ball, an orbit, for instance. Einstein realized, with breathtaking clarity and elegant mathematical formulation, that mass and energy in the universe don't exert a mysterious instantaneous force across empty space, pulling objects towards them, as Newton had conceived. Rather, they curve spacetime itself. The presence of mass and energy warps and distorts the very fabric of the cosmos, making it no longer flat, but curved, much like the bowling ball warps the rubber sheet. Free-falling objects, whether an apple falling from a tree or a planet orbiting a star, then simply follow the straightest possible paths, what mathematicians call geodesics, within this newly curved spacetime. What appears to us as a gravitational force, a mysterious pull, is merely the elegant, unavoidable manifestation of spacetime's intrinsic geometry. The objects responding to the hills and valleys of the cosmic fabric, following the natural contours of reality itself. We don't fall because we're pulled. We fall because the path ahead is bent. Even those seemingly stubborn phenomena known as tidal forces, those subtle yet powerful variations in gravity across a finite body, like the differential pull of the moon on Earth's oceans, causing the ebb and flow of tides on both sides of the planet, which might initially appear to challenge the elegant simplicity of the equivalence principle, actually serve to deepen our understanding. Tidal forces are not, in fact, local forces, acting uniformly on every single point of an object. Instead, they are a direct manifestation of the non-uniformity of spacetime curvature across a region. One side of a large object, being slightly closer to the source of gravity, might feel a slightly stronger pull than the other side, or different parts of a fluid body might experience differential stretching or compressing forces. These differential forces cannot be eliminated by simply accelerating a frame of reference. The equivalence principle, strictly speaking, applies only to infinitesimally small regions of spacetime, where the curvature is so slight that the region can be considered locally flat, like a tiny patch on the surface of the Earth appearing flat, even though the Earth itself is a large sphere. Over larger scales, the varying curvature, the nuances of the geometric landscape, reveal themselves, giving rise to these powerful and observable tidal effects, showing us that gravity is truly about the shape of space, not just a simple, uniform pull. Einstein's monumental theory of general relativity, finally unveiled in its full glory in 1916, thus completely revolutionized our understanding of gravity, replacing Newton's concept of a mysterious, instantaneous force with this dynamic curvature of space-time. At its heart lies his famous set of field equations, a profound and elegant mathematical statement. Curvature of space-time equals constant times matter. The matter side of this equation is not just about tangible objects like stars and planets, but includes all forms of energy and pressure. For according to Einstein, energy is mass, and all possess mass energy, and thus influence space-time's geometry. This equation fundamentally asserts a reciprocal dance, a cosmic dialogue. Matter and energy tell space-time how to curve, and in turn, the curved space-time tells matter and energy how to move. It is a cosmic ballet, a self-regulating, self-consistent system where cause and effect flow dynamically. The profound beauty and complexity of this theory lie in its inherent self-interaction. Space-time curvature itself represents a form of energy, gravitational energy, and as such, it generates its own gravitational field, which in turn causes further curvature, creating a wonderfully complex, self-referential system where gravity is not just a force, but an aspect of the medium itself. And crucially, unlike Newton's instantaneous action at a distance, where gravity seemed to operate across vast distances without delay, general relativity predicted that gravity, or more accurately, space-time curvature, propagates at the finite speed of light. This prediction of gravitational waves, ripples in space-time itself, carrying energy away from accelerating masses, was a radical departure. Its experimental confirmation came decades later, most notably through the meticulous observation of binary pulsars, like the Hulse-Taylor system. These cosmic pairs of rapidly rotating neutron stars gradually lose orbital energy by emitting gravitational waves, causing their orbits to slowly, imperceptibly shrink. A precise, stunning confirmation of this exquisite aspect of general relativity, a triumph of theoretical prediction meeting observational reality. The recent direct detection of gravitational waves by LIGO from merging black holes further cemented this triumph, allowing us to hear the universe's gravitational symphony. Even with this revolutionary achievement, Einstein, ever the visionary, felt his theory was incomplete, a stepping stone on a larger path. He harbored an unfulfilled yearning for a unified field theory, a grand synthesis that would merge gravity, his geometric force, with electromagnetism, and perhaps all other fundamental forces of nature, into a single, elegant, geometric framework. He sought a single, all-encompassing equation that would describe everything, from the smallest particles to the largest galaxies. While his lifelong quest for such a grand unification remained unfulfilled within his lifetime, it nonetheless laid the conceptual groundwork for the tireless efforts of modern physicists who continue today to seek a theory of everything, a grand design to unify all forces into a single, cohesive picture of reality. Some of these modern theories even propose that matter itself, in its deepest essence, might ultimately be a complex manifestation of spacetime's inherent geometric properties, a dance of curvature at the quantum scale, where the very particles we observe are but intricate folds and ripples in the cosmic fabric. General relativity has passed an impressive array of stringent observational tests with flying colors, proving its profound accuracy and predictive power time and again. The precise deflection of starlight grazing the limb of the sun during a solar eclipse, famously observed by Eddington's expeditions in 1919, and confirming Einstein's prediction of twice Newton's value for light bending, was a dramatic, front-page validation that catapulted Einstein to global fame. The anomalous precession of Mercury's orbit, a tiny but persistent deviation in its elliptical path that Newton's theory could not explain, found its elegant and precise solution within the framework of general relativity. And the minute gravitational redshift of light, where photons lose energy and shift to redder wavelengths as they escape a strong gravitational field, has also been confirmed with exquisite precision. Each test, each new observation, only deepens our awe at the profound and beautiful reality Einstein uncovered, confirming that gravity is indeed the curvature of spacetime, a truly elegant and beautiful cosmic truth. A historical precursor to Einstein's thought, a concept that profoundly influenced him in his early formulations, was Mach's principle. This principle, articulated by the physicist and philosopher Ernst Mach, posited a radical idea that all inertial forces, those resistances to acceleration we feel, like the centrifugal force that pushes us outwards when turning a corner in a car, or the force that keeps a spinning object from simply flying apart, arose not from some absolute fixed space, as Newton believed, but from the collective gravitational influence of all matter in the distant universe. Imagine the stars and galaxies, however distant, somehow collectively defining a local frame of reference. Newton, with his famous rotating bucket experiment, where a bucket of water when spun has its surface climb the walls due to centrifugal force, even if initially stationary relative to the bucket itself, suggesting an absolute frame of reference independent of other matter, had argued compellingly for the existence of absolute space. But thinkers like George Berkeley and Mach, in contrast, asserted that motion, especially rotation, was intrinsically meaningless without other matter as a reference point. Einstein was deeply influenced by this idea, initially believing that general relativity would inherently embody Mach's principle, suggesting that the spacetime metric was entirely determined by the distribution of matter. However, as the theory matured and its solutions were explored, it became clear that spacetime possessed an independent reality. It could exist and exhibit curvature and dynamics, even in the complete absence of matter, as in the de Sitter universe, which contains no matter but expands. This led Einstein, with some reluctance, to ultimately abandon a strict interpretation of Mach's principle. Yet, the core idea of a universe where geometry and matter are inextricably linked, where the local dynamics are subtly shaped by the global distribution of mass and energy, remains a powerful undercurrent in cosmological thought, hinting at a deep interconnectedness across cosmic scales. And so, as we continue our gentle descent into the quiet realms of cosmic contemplation, our minds turn now to one of the most enigmatic, awe-inspiring, and frankly terrifying predictions of general relativity: the black hole. These cosmic enigmas represent the ultimate triumph of gravity, regions of space-time where the fabric of reality is so profoundly warped that nothing, not even light, can escape their relentless grip. The story of a black hole begins, ironically, with the incandescent, vibrant lives of stars, those luminous, burning globes of gas that light up our night sky and give life to the universe. For most of their long existence, stars exist in a delicate, precarious balance, a cosmic tug-of-war. On one side, there is the immense inward pull of their own self-gravity, relentlessly trying to crush them into oblivion. On the other, there is the powerful outward push of internal pressure, generated by the searing heat of nuclear fusion reactions in their cores, where hydrogen is transmuted into helium, releasing colossal amounts of energy, a constant battle between collapse and expansion. But this nuclear fuel, the hydrogen and helium that feed their brilliance, is finite. Eventually, inevitably, the fusion reactions in the cores cease. When a star exhausts its primary hydrogen fuel, its core begins to contract under the relentless grip of gravity, causing temperatures to rise sufficiently to ignite heavier elements like helium, then carbon, and so on, in a desperate attempt to create new pressure. This initiates a complex series of evolutionary stages, transforming the star into a luminous red giant or even a supergiant, its outer layers expanding dramatically. For smaller stars, those roughly up to 8 times the mass of our Sun, their ultimate fate is to become white dwarfs, incredibly dense remnants, roughly the size of Earth, whose gravity is finally supported by the quantum mechanical phenomenon of electron degeneracy pressure, a subtle but immensely powerful resistance of electrons to being packed too closely together, a force of quantum repulsion. More massive stars, however, face a far more dramatic and violent end. Their cores contract further and further, igniting ever heavier elements up to iron in a desperate last-ditch attempt to stave off gravitational collapse, creating layers of burning elements like an onion. This process culminates in a cataclysmic supernova explosion, a cosmic detonation that can briefly outshine an entire galaxy, scattering newly forged heavy elements across the cosmos. This titanic explosion often leaves behind a rapidly rotating, incredibly dense core known as a neutron star, a sphere perhaps only 10 to 20 kilometers in diameter, but containing the mass of a sun or more, where gravity is held at bay by the even stronger neutron degeneracy pressure, the quantum repulsion of neutrons. These neutron stars are often observed as pulsars, sending out regular, precisely timed beams of radio waves as they spin furiously. But for the most massive stars, those born with initial masses perhaps 20 to 30 times that of our Sun, even the formidable neutron degeneracy pressure proves insufficient to withstand the relentless, crushing grip of gravity. In such extreme cases, after the supernova explosion blasts away the star's outer layers, the remaining stellar core implodes utterly, uncontrollably, collapsing beyond all known limits of density and pressure. It collapses past the point where even neutrons can resist compression, leading to the dramatic and irreversible birth of a black hole. To a hypothetical observer falling with the collapsing core, moving freely along with the infalling matter, the collapse itself would be swift and perhaps uneventful, a feeling of perpetual freefall. This journey culminates in a singularity, a theoretical point of infinite density and zero volume, where space-time curvature becomes infinite, and all our known laws of physics, as we currently understand them, spectacularly break down. It is a boundary beyond our comprehension, a realm of ultimate compression, where the very fabric of reality is infinitely distorted, a tearing of the cosmic cloth. But to a distant observer, standing safely far away in ordinary space-time, the story unfolds quite differently, a strange and distorted cosmic ballet that seems to defy the passage of time. As the collapsing star shrinks and approaches a critical size, known as the Schwarzschild radius, a specific radius unique to each black hole determined by its mass, where the escape velocity, the speed needed to overcome its gravity and break free, precisely equals the speed of light. Its emitted light is increasingly stretched, or redshifted, towards longer, redder wavelengths, losing more and more energy as it fights to escape the immense gravity. The star appears to darken, redden, and, from our distant perspective, its collapse seems to freeze in time, becoming infinitely slow as light struggles to escape. Eventually, the last photon struggles free, and the star crosses this boundary, becoming a black hole, its ultimate collapse and the formation of the singularity forever hidden from external view. This boundary, the event horizon, is not a physical surface that one would feel or see as a tangible barrier. Rather, it is a one-way membrane in space-time, a point of no return. Anything, matter, energy, light itself, can fall in, but absolutely nothing, not even a single photon, can escape once it crosses this critical threshold. It marks the edge of the observable universe from the perspective of an external observer, defining what can ever return to us. The space-time around a black hole is not merely curved. It is profoundly, violently warped and twisted, a cosmic vortex. The light cones, those abstract representations that in ordinary flat space-time define the possible future paths of light, and, by extension, all physical objects, tilt ever more steeply and dramatically towards the black hole as one approaches the event horizon. Within the event horizon, a future light cone tips so far inward that all possible paths for light and matter lead inexorably towards the central singularity, and none, not a single one, lead back out towards the external universe. It's a cosmic cul-de-sac, a gravitational trap from which there is no exit. This tilting also implies something even more mind-bending. That space itself, in a very real and measurable sense, effectively flows into the black hole, much like water down a drain. With the speed of this flow reaching the speed of light at the event horizon, this strange phenomenon is often described as the, quote, country of the Red Queen, a whimsical yet accurate reference to Lewis Carroll's Through the Looking Glass, where the Red Queen tells Alice, "It takes all the running you can do to keep in the same place." Here, at the event horizon, one must, in effect, move inward at the speed of light, simply to stand still relative to the relentless, infalling current of space. An astonishing, mind-bending consequence of warped space-time. While the simplest black holes, those that are non-rotating, are predicted to be perfectly spherical, their simple, elegant form is a consequence of the celebrated no-hair theorem. This remarkable theorem, articulated by physicist John Wheeler, implies that once a black hole has settled down after its formation, it loses almost all information about the specific star or matter from which it formed. It is defined by only three external measurable properties: its total mass, its electric charge, though cosmic objects rarely accumulate significant net charge due to their immense gravity, and its angular momentum, its spin. All other intricate information about the star's composition, its precise shape, its magnetic fields, or the details of its collapse, is either radiated away into space-time or falls irrevocably into the black hole, lost to the external universe, forever hidden behind the event horizon. While electric charge is rare in cosmic objects, most stars rotate, so rotating black holes, also known as Kerr black holes, are widely believed to be the most common type in the universe, as angular momentum is generally conserved. Described by the intricate and highly complex Kerr metric, these spinning black holes distort space-time in even more complex and fascinating ways than their non-rotating counterparts. They create an additional, profound region beyond the event horizon called the, quote, ergosphere. This is a bizarre region where space-time itself is dragged into rotation by the spinning black hole's immense gravitational pull, forming a kind of cosmic whirlpool from which, theoretically, energy can be extracted from the black hole's rotational energy, a process known as the Penrose process, hinting at a way to harness their immense power. Black holes grow, steadily increasing their mass, primarily through the process of accretion, the gravitational drawing in of surrounding gas, dust, and even other stars. This infalling matter does not simply vanish. It typically forms a superheated, rapidly swirling accretion disk around the black hole, frictional forces heating it to millions of degrees, causing it to glow brightly across the electromagnetic spectrum. often producing powerful jets of high-energy particles that blast outward into space, extending for light years. In the nuclei of most large galaxies, this accretion process can lead to the formation of truly colossal supermassive black holes, millions or even billions of times the mass of our Sun. These gargantuan objects are believed to be the engines powering some of the most energetic phenomena in the universe, such as quasars and active galactic nuclei, which can outshine entire galaxies. Surprisingly, these supermassive black holes have incredibly low average densities, sometimes even less dense than air for the very largest ones, due to their immense volume. This means that, in principle, an astronaut could cross the event horizon of a supermassive black hole without immediately being torn apart by tidal forces, which are weaker at the horizon for larger black holes. The stretching force is distributed over a larger region. They would simply experience a rapid, irreversible journey to the singularity, a journey from which no light or signal could ever return to tell the tale, a one-way trip into the unknown. And what of mini-holes? While the conditions required for their formation are unlikely to arise from the collapse of individual stars today, tiny, primordial black holes might have been forged in the unimaginably extreme and dense conditions of the very early universe, perhaps in the first fleeting moments of the Big Bang, from extreme density fluctuations. A mini-hole, if it existed, could be as small as a nucleon, yet possess an astonishing mass, perhaps 10 to the power of 15 grams, equivalent to 1 billion tons packed into a subatomic space. A tiny, ultra-dense cosmic bullet. The most astonishing and revolutionary discovery concerning black holes, however, came from the brilliant theoretical physicist Stephen Hawking in 1974. He demonstrated, through a profound application of quantum field theory in curved spacetime, that black holes are not truly black in the absolute sense, but rather that they emit a faint thermal glow. This Hawking radiation, as it is called, arises from subtle quantum mechanical effects near their event horizons, essentially revealing that black holes possess a temperature. This temperature is inversely proportional to their mass, meaning smaller black holes are hotter and thus radiate energy at a faster rate. Mini-holes, being incredibly hot, would radiate intensely and quickly, losing mass and eventually evaporating entirely in a colossal burst of high-energy particles, a miniature cosmic fireworks display. This profound insight implies that black holes are not eternal, information-destroying sinks, but rather dynamic heat engines that generate entropy, slowly but inexorably transforming all forms of mass energy into radiation. This radically altered our understanding of black holes, linking them inextricably to the deep principles of thermodynamics and quantum mechanics, suggesting a beautiful, if terrifying, cosmic life cycle, even for these ultimate devourers of light and space. And now, as our thoughts gently expand with the universe itself, let us turn to one of the most pivotal discoveries in all of cosmology, one that redefined our place and perspective within the cosmos. The path to this monumental insight was paved, in part, by a familiar phenomenon from our everyday world: the Doppler effect. This effect, where the frequency of a wave changes as its source moves relative to an observer, is readily observed in the changing pitch of a siren as it approaches and recedes, or the shift in a train whistle's tone. As early as 1912, the pioneering American astronomer Vesto Slipher, working with meticulous spectroscopic observations at the Lowell Observatory, began to notice something profoundly peculiar about the light emanating from most of the faint, fuzzy celestial objects then called spiral nebulae, which we now know to be distant galaxies, entire island universes unto themselves. He observed that their distinctive spectral lines, the unique chemical fingerprints embedded in their light, like a cosmic barcode revealing their composition, were systematically redshifted, meaning they were stretched towards longer, redder wavelengths of the electromagnetic spectrum. This redshift, according to the well-understood Doppler effect, was interpreted as a sign of recession velocity. These nebulae, these vast collections of stars, were moving away from us at astonishing speeds, many thousands of kilometers per second. This was deeply puzzling at the time. If the motions of galaxies were purely random, one would naturally expect an equal number to be blue-shifted, moving towards us. The overwhelming prevalence of redshifts, however, hinted at a deeper, more systematic, and highly ordered motion underlying the entire cosmos, a collective exodus. The first theoretical hints of a dynamic, non-static universe, a concept radical for its time, emerged a few years later. In 1917, the Dutch astronomer Willem de Sitter, delving into the intricate mathematical framework of Einstein's newly formulated general relativity, predicted a systematic redshift from distant nebulae, even in his theoretical model of an empty, static-appearing universe. This hypothetical de Sitter universe was an elegant solution to Einstein's equations that implied a cosmic expansion without the presence of any actual matter, driven by a cosmological constant. Einstein himself, originally a strong proponent of a static, eternal universe, a belief deeply ingrained in philosophical traditions that saw the universe as unchanging, had been so convinced of this that he controversially introduced a term into his field equations known as the cosmological constant, often denoted by the Greek letter lambda. This lambda force was conceived as a repulsive force, a kind of cosmic anti-gravity, specifically intended to counteract the attractive force of ordinary gravity, and thus keep the universe from collapsing under its own weight, ensuring its static nature. However, it was the brilliant Russian mathematician Alexander Friedmann, in his groundbreaking papers of 1922 and 1924, and independently, the visionary Belgian priest and physicist Georges Lemaitre in 1927 and 1931, who developed more general non-static solutions to Einstein's equations. Their groundbreaking work demonstrated unequivocally that the universe could, and indeed should, be either expanding or contracting. A static universe, they showed, was an unstable, fleeting possibility, a cosmic balancing act that couldn't last, like a pencil balanced on its tip. Then, the moment of revelation arrived. In 1929, the American astronomer Edwin Hubble, working with powerful telescopes at the Mount Wilson Observatory, made his momentous, career-defining discovery through meticulous observations of Cepheid variable stars in distant galaxies. These pulsating stars served as his crucial standard candles, objects of known intrinsic brightness that allowed him to gauge their distance. He announced to the world the profound empirical relationship. Galactic redshifts increase proportionally with distance. The farther away a galaxy was, the greater its redshift, and thus, by the accepted Doppler interpretation of Slipher's work, the faster it appeared to be receding from us. This empirical relationship, now universally known as Hubble's law, often expressed as ZC equals HL, where Z is the redshift, C is the speed of light, H is the Hubble term or Hubble constant, and L is distance, coupled with the Doppler interpretation, led directly to the profound velocity-distance law, V equals HL. The implications were staggering, reorienting humanity's cosmic perspective. The more distant a galaxy, the faster it recedes from us. The universe, it seemed, was not static, nor were galaxies merely hurtling randomly through a fixed space. The entire cosmos was in a state of grand, systematic expansion, unfolding before our very eyes. This was the moment we truly understood our place in a dynamic, evolving cosmos. From this pivotal discovery, the expanding space paradigm gradually and profoundly emerged, reshaping our cosmic intuition and challenging our everyday understanding of motion. This concept clarifies that the universe is not merely expanding into some pre-existing larger space, like a conventional explosion radiating outwards into an empty room. Rather, the universe is the space, and it is space itself that is expanding, stretching, and carrying the galaxies along with it. Galaxies are not hurtling through space in the conventional sense, as if they were projectiles launched from a central point. Instead, they are largely at rest relative to the expanding fabric of space, being passively carried apart as the cosmic metric, the very ruler of space, stretches. This profound concept is vividly illustrated by the widely used analogy of the expanding rubber sheet universe, ERSU. Imagine dots painted on the surface of a stretching rubber sheet. As the sheet is pulled and expands uniformly, the dots move farther apart from one another. Crucially, the dots themselves are not moving on the sheet through any intrinsic propulsion. They are simply being carried along by the stretching of the sheet beneath them. This visual metaphor elegantly captures the essence of cosmic expansion, where the distances between unbound objects grow not because they are moving, but because the space between them is growing, carrying them along. This observed phenomenon of homogeneous and isotropic expansion, meaning it appears the same everywhere we look and in every direction we gaze on sufficiently large scales, leads directly to the linear velocity distance law that Hubble empirically discovered. The constant of proportionality in this relationship, h, is known as the Hubble term, or Hubble constant, and it serves as a measure of the current rate at which the universe is expanding. Its precise value has been a subject of intense debate and refinement over decades, as even small variations have significant implications for cosmic age and evolution. Its reciprocal, the Hubble time, th equals 1h, provides a rough order of magnitude estimate of the universe's age, assuming a constant expansion rate, though the actual age is more complex due to cosmic acceleration and deceleration. Furthermore, the distance at which the recession velocity of a galaxy, due to this expansion, would theoretically equal the speed of light, v equals c, defines the Hubble length, LH equals c times ch, also sometimes referred to as the boundary of the Hubble sphere. It is a crucial point to grasp that galaxies beyond this Hubble sphere can and do recede from us at speeds faster than light, and this does not violate Einstein's special relativity. This is because special relativity governs the motion of objects through space, not the expansion of space itself. The space between us and these distant galaxies is simply stretching so rapidly that the galaxies are carried away faster than light can traverse the expanding distance. The expansion rate of the universe is not necessarily constant throughout cosmic history. It has changed and continues to change, a dynamic process rather than a steady march. The deceleration term q is a dimensionless parameter that describes how this expansion is changing over time, whether it is slowing down, if q greater than 0 due to the gravitational pull of matter and radiation, or speeding up, if q less than 0 due to some mysterious repulsive force, such as the enigmatic dark energy. This term is critically important as it dictates the universe's ultimate kinematic fate. Will it continue to expand forever, or will it eventually halt and begin to contract? Its value, which current observations indicate is negative, implying acceleration, profoundly impacts our models of the cosmos and its distant future, suggesting a universe that will expand forever, at an ever-increasing rate. Universes are broadly classified by their geometry, flat, spherical, or hyperbolic, indicated by the constant k in the Friedmann equations. Their kinematics, the history of their expansion or contraction, often described with dramatic terminology like bang and whimper cycles, and their dynamics, The intricate interplay of matter density, radiation density, and the cosmological constant lambda, which dictates the gravitational forces at play, including the accelerating These classifications allow cosmologists to explore a vast parameter space of possible cosmic histories, mapping out the theoretical landscape of universes, each a potential cosmic story. And as the universe expands around us, carrying galaxies further into the cosmic night, it leaves an indelible signature upon the light that travels to us. This signature, the cosmic redshift, is one of the most powerful diagnostic tools in modern cosmology, offering a direct window into the universe's history, a cosmic timestamp encoded in every photon. As light embarks on its immense journey across the vast, expanding expanse of space, its wavelengths are literally stretched out, elongated in precise proportion to the overall expansion of the universe during its travel time. Imagine a wave drawn on a rubber band. As the rubber band stretches, so too does the wavelength of the wave drawn upon it. If, for instance, the universe has doubled in size since a distant galaxy emitted its light, then all the wavelengths of that light will also be doubled, appearing twice as long, and thus shifted towards the red end of the electromagnetic spectrum. This expansion redshift law, mathematically expressed as 1 plus z equals r/r, where z is the redshift, r is the scale factor of the universe at the time we observe the light, and r is the scale factor when the light was emitted, directly provides a precise measure of how much the universe has expanded since that light left its cosmic source. A quasar, for example, observed with a redshift of z equals 2, tells us that the universe is now 3 times larger, 1 plus 2 equals 3, than it was at the moment that ancient light was emitted, billions of years ago. This stretching of light also carries another profound implication. It means cosmic time itself is stretched. Events observed in very distant high redshift galaxies appear to unfold more slowly, or time-dilated, the farther back we look. A phenomenon that intrinsically lasts for 1 second in a galaxy at a redshift of z equals 1 will appear to us to last for 2 seconds, an observational effect that has been strikingly confirmed in the light curves of distant supernovae. This cosmic time dilation is a direct, observable consequence of the expanding space, a universe unfolding in slow motion from our distant perspective. It is absolutely crucial, for a precise and accurate understanding of cosmology, to meticulously distinguish between the, quote, 3 distinct types of redshift that astronomers observe, as they arise from fundamentally different physical processes. First, there is, quote, gravitational redshift. This subtle but measurable effect occurs when light, or any form of electromagnetic radiation, climbs out of a strong gravitational field. As photons expend energy to escape the immense pull of gravity, their energy decreases, which in turn causes their wavelength to increase, shifting them towards the red end of the spectrum. This effect is subtle but measurable, for instance, in light escaping from massive stars, white dwarfs, or even with incredibly precise atomic clocks, when comparing clocks at different altitudes in Earth's gravitational field. Second, we have Doppler redshift. This is the more familiar effect from everyday experience, caused by the relative motion of an object through space, often called its peculiar velocity. If a galaxy is moving away from us through static space, the light waves it emits are stretched, much like the pitch of a siren drops as it moves away. Conversely, if an object is moving towards us, its light is blue-shifted. This type of redshift is governed by the principles of special relativity and is typically what we measure for nearby galaxies, whose individual motions, their peculiar velocities, relative to the Hubble flow, dominate over the expansion of space itself. Third, and most fundamentally important for understanding the large-scale structure and evolution of the universe, is the expansion redshift. This is the redshift caused purely by the expansion of space itself, carrying galaxies along with it, often referred to as, quote, recession velocity. This effect is governed by the equations of general relativity, and it is the dominant contributor to the redshifts observed for very distant galaxies. It's not the galaxies moving through static space that causes this redshift. Rather, it's the stretching of the space between us and the distant galaxy that elongates the wavelengths of light traveling through it. This is the cosmic stretch, the primary indicator of our expanding universe. Confusing expansion redshift with Doppler redshift is a common cosmological pitfall, one that can lead to erroneous and misleading interpretations. For example, if one misinterprets the superluminal recession of distant galaxies, where space expands between them faster than light speed, as measured by our coordinate system, as galaxies moving through space faster than light, it would appear to violate Einstein's special relativity, which sets, quote, c as the ultimate speed limit within spacetime. Similarly, such a misunderstanding could lead to the false notion of a cosmic edge or a center of explosion in the universe, as if galaxies were flying away from a single point, rather than space expanding everywhere, uniformly. The linear Hubble law, ZC equals HL, is, in fact, only an accurate approximation for galaxies at relatively small redshifts, typically Z less than about 0.1, in our immediate cosmic neighborhood. Beyond this immediate region, the relationship between redshift, distance, and velocity becomes nonlinear and much more complex. It must be accurately calculated within the rigorous framework of a specific cosmological model, such as the Einstein de Sitter universe, which accounts for the intricate geometry and dynamics of expanding spacetime, providing a more precise cosmic map. Throughout the history of cosmology, alternative explanations for redshift have been proposed, challenging the dominant expansion paradigm. One such class of ideas involves tired light theories, which posited that light simply loses energy, or gets tired, as it travels over vast distances through the cosmos, without any expansion of space, perhaps through some unknown interaction with intergalactic matter. However, these theories fail spectacularly on multiple observational fronts. They cannot explain the perfectly thermal black-body spectrum of the cosmic background radiation, which is a signature of an expanding, cooling universe that was once in thermal equilibrium. Nor can they account for the observed time dilation of distant supernova light curves, which is a direct consequence of expansion, or the absence of detectable scattering that such energy loss mechanisms would imply. If light were being scattered, we would expect images of distant galaxies to appear much fuzzier than they do. Another intriguing, though highly controversial challenge to the Standard Model came from Halton Arp's observations of, quote, discordant redshifts. Arp found instances where objects that appeared to be physically connected, such as quasars seemingly ejected from active galactic nuclei, exhibited vastly different redshifts, suggesting some objects might possess non-cosmological redshifts, implying physics beyond the Standard Model. While these observations continue to stimulate debate and encourage scrutiny, the vast majority of cosmologists offer alternative explanations, often involving chance superposition of objects along the line of sight, or complex local interactions that mimic physical connection. The Standard Model, despite these fascinating challenges, remains overwhelmingly supported by the weight of diverse and consistent observational evidence, a testament to its explanatory power. As we settle deeper into this cosmic journey, let's consider a fascinating historical detour, a curious harmony between the old and the new. Even before the advent of modern cosmology and Einstein's profound insights into curved spacetime, Isaac Newton, in his monumental wrestling with the universal force of gravity, encountered what we might call the gravity riddle. In a universe that he conceived as infinite, static, and uniformly filled with matter, how could the stars avoid collapsing inward under their own immense mutual gravitational attraction, inevitably coalescing into a single colossal mass? And, conversely, why didn't infinite gravitational forces pull from every conceivable direction, rendering any stable configuration of matter impossible, literally tearing everything apart? Newton, in a brilliant stroke of philosophical and mathematical insight, found a conceptual solution by assuming perfect homogeneity and isotropy on a cosmic scale. That matter was distributed absolutely uniformly throughout an infinite space, such that the infinite forces from every direction would, in theory, precisely cancel each other out, leading to a net zero force at any given point. This mental construct, though perhaps physically tenuous in practice, allowed for a universe that, at least from a gravitational perspective, could remain stable and avoid catastrophic collapse. A few decades later, Edmund Halley, famous for his eponymous comet, extended this line of reasoning to light, pondering a similar, unsettling paradox. If the universe were truly infinite, uniformly populated with an eternal distribution of luminous stars, then, logically, every single line of sight from Earth should eventually terminate on the surface of a star. This would, by all accounts, lead to an infinitely bright night sky, blazing with light from every direction, utterly contradicting the obvious and serene observation of darkness at night. This profound dilemma, though not fully formalized until the 19th century by Olbers, became known as Olbers' paradox. Surprisingly, given the immense conceptual leap from Newtonian gravity to Einstein's general relativity, a fascinating and rather unexpected intellectual concordance emerged in 1934. The British astrophysicists Edward Milne and William McCrea demonstrated, with remarkable clarity, that the fundamental equations governing the dynamics of a uniform, expanding universe, equations that had previously been derived from the mathematically complex framework of general relativity, could, under certain ideal conditions and specific interpretations, be reproduced using only the relatively simple principles of classical Newtonian physics. Imagine for a moment a finite, uniformly dense sphere of matter, expanding outward into an otherwise empty Euclidean space. One could then analyze the motion of particles located at its surface. Depending on the initial kinetic energy of these particles relative to the gravitational pull of the sphere's total mass, their trajectories would follow distinct paths. An elliptical path, where the expansion eventually halts and reverses into a collapse. A parabolic path, representing a universe that expands just enough to escape gravity's grip, asymptotically slowing to a halt after infinite time. Or a hyperbolic path, signifying an ever-expanding universe, overcoming gravity with ample kinetic energy to expand indefinitely. These three Newtonian kinematic possibilities precisely correspond, with astonishing fidelity, to the closed, spherical, flat, Euclidean, or open, hyperbolic geometries of the Friedmann universes, in the framework of general relativity. This profound and initially perplexing concordance between the classical and relativistic cosmologies, a testament to the underlying simplicity in complex systems, is understood by realizing that Newtonian theory, when applied accurately to small, local regions of a uniform universe, can approximate the dynamics of the global relativistic expansion, despite their foundational differences in conceptualizing gravity itself. It shows that sometimes, simpler models can capture the essence of deeper truths. The, quote, cosmological constant, lambda, that controversial term introduced by Einstein into his equations to force a static universe, also found an intriguing and useful interpretation within this Newtonian analogy. In Newtonian terms, lambda effectively acts as a repulsive force, a form of anti-gravity that pushes matter apart, counteracting the attractive force of ordinary gravity. Its inclusion in the mathematical framework yielded the Friedmann-Lemaitre equations, a set of elegant differential equations that describe the expansion of space in homogeneous and isotropic models of the universe. These equations, derived from general relativity but having a surprisingly robust Newtonian analog, vastly expanded the range of possible cosmic histories, allowing for universes that could accelerate, decelerate, or even remain static under specific, finely tuned conditions, thus encompassing a far richer tapestry of cosmic evolution than previously imagined by either Newton or the early Einstein. To simplify the intricate study of an expanding universe, and to make its vastness more amenable to the rigorous application of physical laws, cosmologists employ a powerful conceptual tool, a mental construct, the cosmic box. Imagine, if you will, an imaginary, perfectly reflecting, purely theoretical cubical volume. The crucial aspect of this box is that it is co-moving, meaning its boundaries are not fixed in ordinary space, but expand along with the fabric of the universe itself, its sides stretching proportionally to the cosmic scale factor, so that objects within it that are not gravitationally bound remain in the same relative position. This cosmic box is not a physical container in space, existing independently of the universe. Rather, it is a conceptual sample, a representative parcel of the universe, carefully chosen to be large enough to encapsulate the average properties of the cosmos, to ensure homogeneity and isotropy on its scale, yet small enough that we can still apply ordinary physics and Euclidean geometry to the interactions within it, without immediately being overwhelmed by the complexities of global curvature or relativistic effects. It is, in essence, the, quote, universe in a nutshell, a manageable microcosm of the grander whole, a theoretical laboratory of the cosmos, where the complex dance of cosmic evolution can be studied in a simplified, yet accurate manner. This conceptual cosmic box reveals profound insights into the behavior of matter and energy within an expanding cosmos. For instance, freely moving particles within such an expanding volume, particles like individual galaxies, which are generally not moving through space with high velocities of their own, their peculiar velocities, but are primarily carried along with it by the expansion, gradually lose their peculiar motion over time. Their individual velocities relative to the overall cosmic expansion are damped down, causing them to slow down and become increasingly co-moving with the general flow of the universe, riding the expansion. This means that, over vast timescales, any initial random motions tend to be diluted by the expansion, and galaxies become better and better tracers of the underlying cosmic flow, like dust motes in an expanding gas. Their momentum, mu, where m is mass and u is peculiar velocity relative to the co-moving frame, is found to vary inversely with the scale factor r, mur equals constant, a direct consequence of the stretching of space itself. Light waves, too, are intimately affected by this expanding container. As they traverse the cosmic box, their wavelengths are stretched, increasing proportionally with the scale factor r, giving rise to the cosmological redshift we discussed earlier, a beautiful demonstration of the expanding metric affecting light, a cosmic stretching of every photon. Crucially, the concept of the cosmic box allows us to extend the powerful laws of thermodynamics to the universe as a whole, to understand its energy budget, its temperature, and its ultimate fate. Consider a gas or radiation confined within our expanding box. As the box expands, the gas or radiation inside it cools, losing energy. This happens because the internal pressure of the gas or radiation does work against the receding walls of the expanding box, expanding into a larger volume, much like a gas cooling as it expands in an engine. The universe itself being, as far as we know, an isolated system with no external outside with which to exchange energy. It is fundamentally adiabatic, behaves according to these principles. This means that during its expansion, the total energy of the universe, surprisingly, does not remain conserved in the absolute sense we expect in local, static systems. The universe experiences a continuous decrease in its total energy as it expands, a profound departure from the simple energy conservation laws that govern our everyday experience on Earth. However, the venerable second law of thermodynamics, the principle that entropy, a measure of disorder or the amount of energy unavailable for useful work, always increases in isolated systems, still holds true, even on a cosmic scale. The universe as a whole is continuously generating entropy, primarily due to the irreversible processes of stars burning nuclear fuel and radiating light, turning highly organized matter into diffuse energy, and through the gravitational clumping of matter into galaxies and clusters, which, paradoxically, increases the configuration space of the system. The overwhelming majority of the universe's entropy, however, is not found in the relatively paltry output of stars or in the structured complexity of galaxies. Instead, it resides in the ancient, diffuse cosmic background radiation, the faded, homogeneous afterglow of the Big Bang itself, a vast sea of photons carrying the thermal history and the immense entropy of the universe, a silent testament to its past. As our understanding deepens, we begin to appreciate the rich theoretical landscape that cosmology has explored, unveiling a breathtaking gallery of possible universes, each a distinct tapestry woven from the intricate threads of mathematics and physics. For a long time, the dominant paradigm, fueled by ancient philosophical traditions that valued stability, was that of static universes. Einstein himself, as we've already observed, initially conceived of such a model for his general relativity, a closed, spherical universe, gravitationally poised, and held in an incredibly delicate, inherently unstable equilibrium by the precise counterbalance of his then controversial cosmological constant lambda. If anything perturbed it, it would either collapse or expand indefinitely. Another fascinating, albeit ultimately disproven static model was Macmillan's perpetual motion steady-state universe, which proposed a continuous cycling of matter from light energy to form new stars and galaxies, a cosmic recycling plant that would keep the universe eternally unchanging in its average properties. However, these static visions eventually gave way, pushed aside by accumulating observational evidence, such as the redshifts of galaxies proving expansion, and the inherent theoretical instability of such finely balanced systems, yielding to the dynamic models that now dominate our understanding. Among the earliest and most influential dynamic models, those that truly broke the static paradigm, were the de Sitter universe and the Friedmann universes. The de Sitter universe, a peculiar but mathematically elegant solution to Einstein's equations, describes an empty, flat universe that expands exponentially, driven solely by the cosmological constant lambda. It is a universe accelerating into an infinite future of ever-increasing emptiness, devoid of matter but full of expansion, a universe that is everywhere but contains nothing. More central to our current understanding are the Friedmann universes, which represent a family of solutions where the cosmological constant lambda is initially set to 0. Lambda equals 0. These models are rigorously categorized by their intrinsic spatial curvature, denoted by the constant k. K equals 1 describes a closed spherical universe that is spatially finite, like the surface of a globe, and destined to eventually recollapse in a big crunch. K equals 0 describes a flat, infinite universe that expands forever, but asymptotically slows to a halt after an infinite amount of time. And K equals -1 describes an open, hyperbolic universe that is also spatially infinite and expands forever. These Friedmann models, each a distinct cosmic narrative, paint a spectrum of cosmic destinies, ranging from the dramatic bang-bang or closed oscillating scenarios to the eternally expanding whimper of open universes, each with its own beginning and end, or lack thereof. Lemaitre, in his creative exploration of these possibilities, later proposed his own intriguing hesitation universe, a closed model that included a cosmological constant lambda, slightly larger than Einstein's initial value. This led to a period of near-static loitering in its expansion, a kind of cosmic pause, where gravity and lambda were almost perfectly balanced, during which galaxies might have had ample time to form and evolve before the universe resumed its expansion towards an eventual recollapse. Similarly, Sir Arthur Eddington conceived of an anti-bang universe, one that began in a delicate static Einstein state, only to be perturbed by some cosmic fluctuation, causing it to embark on a journey of eternal expansion, a slow unraveling rather than a violent birth. These myriad models, each a distinct cosmic narrative, are systematically classified not only by their intrinsic geometry, the value of K and its profound implications for the universe's overall shape and curvature, but also by their kinematics, the entire history of their expansion or contraction, from the initial bang to a potential whimper or recollapse, and by their dynamics, the intricate interplay of matter density and the cosmological constant lambda, which these classifications allow cosmologists to explore a vast parameter space of possible cosmic histories, mapping out the theoretical landscape of universes, each a potential cosmic story, each unfolding according to its own internal logic. Intriguingly, cosmologists have discovered that universes in compression, meaning those dominated by radiation in their very early stages, such as the first few tens of thousands of years after the Big Bang, exhibit a higher effective pressure, P equals rho c squared/3 for radiation. This pressure, perhaps counterintuitively, significantly increases the effective gravitational pull and thus decelerates expansion more effectively and rapidly than matter alone would. It's as if the pressure adds to the gravitational weight of the universe, slowing its outward rush, an extra braking mechanism. Even stranger are universes in tension, which exhibit negative pressure, tilde way equals rhi ho c squared. This bizarre property, rather than resisting expansion, actually accelerates it, pushing spacetime apart. Such negative pressure can lead to scenarios like constant density, exponential expansion, where the universe grows incredibly rapidly while maintaining a steady density, a phenomenon believed to have occurred during the early universe's dramatic inflationary period, which we will discuss shortly. A profound and persistent challenge in cosmology, one that continues to provoke deep thought, is the homogeneity riddle. Why is the universe so remarkably uniform and isotropic on large scales, appearing almost perfectly smooth in its temperature and matter distribution, even between regions that were causally disconnected in the extremely early universe, having never had a chance to interact and homogenize? How could they have reached such an even temperature and density without any physical communication, any exchange of information? The chaos school of thought suggests that the universe might have begun in a state of extreme disorder, but that some cosmic mechanism, through evolution, smoothed out these irregularities. Models like the Mixmaster universes, proposed by Charles Misner, explored how chaos could, paradoxically, lead to homogeneity through complex, anisotropic contraction and expansion cycles near a singularity, mixing the universe into uniformity through sheer complexity. Conversely, the anti-chaos school argues that such remarkable homogeneity is either a fundamental, initial condition of the universe, inherent from its very beginning, or it is a consequence of the anthropic principle that we observe homogeneity precisely because our existence, requiring a relatively smooth universe for stars and galaxies to form, depends on it. We could not have arisen in a wildly chaotic, lumpy cosmos. Beyond these broad categories of geometry and dynamics, other fascinating theoretical frameworks have been explored. Milne's kinematic relativity, for example, offered a unique perspective, providing a universe that, when translated into the language of general relativity, became an infinite, negatively curved universe expanding at a constant rate, continually diluting its matter without ever reaching a singularity, a kind of eternal, lonely expansion. Then there was the highly influential, yet ultimately superseded, continuous creation steady-state universe model, championed by Hermann Bondi, Thomas Gold, and Fred Hoyle in the mid-20th century. This elegant and philosophically appealing model posited a universe that was eternally the same in its large-scale properties, homogeneous, isotropic, and unchanging on average, despite its expansion. To maintain a constant density of matter in an expanding universe, the steady-state theory proposed that new matter was continuously and spontaneously created everywhere in the cosmos, uniformly distributed throughout space, at an imperceptibly slow rate, just enough to replenish the matter diluted by expansion. This model, despite its aesthetic appeal and its elegant simplicity, was ultimately disproven by two monumental discoveries: the detection of the cosmic background radiation in 1964, the definitive afterglow of a hot, dense early universe, and the observation of the evolution of radio sources and quasars, which showed unequivocally that the universe was changing over time, looking different in the distant past than it does today, providing clear evidence for an evolving rather than a steady. Finally, we consider scalar tensor theories, pioneered by Pascual Jordan, and later explored by Hoyle-Narlikar and Bransdieck. These theories present a fascinating cosmic dream machine by suggesting that fundamental constants of nature, such as Newton's gravitational constant g, or the masses of elementary particles, might not be truly constant, but could, in fact, vary with time, or even with position in space. This dynamic variability would mean that the very laws of physics, the rules of the cosmic game, could change over cosmic epochs or across different regions of spacetime, transforming one type of universe into another. While many specific predictions of such theories, such as a measurable variation in g over time, have been disproven by precise observational data, these theories continue to inspire and explore the very flexibility of natural law, pushing the boundaries of what we consider fundamental and immutable about the cosmos. They remind us that our current understanding, while powerful, may still be but one chapter in a much larger cosmic story, a story where even the constants might not be so constant after all. As our understanding deepens, we begin to appreciate the rich theoretical landscape that cosmology has explored, unveiling a breathtaking gallery of possible universes, each a distinct tapestry woven from the intricate threads of mathematics and physics. For a long time, the dominant paradigm, fueled by ancient philosophical traditions that valued stability, was that of static universes. Einstein himself, as we've already observed, initially conceived of such a model for his general relativity, a closed, spherical universe, gravitationally poised, and held in an incredibly delicate, inherently unstable equilibrium by the precise counterbalance of his then controversial cosmological constant lambda. If anything perturbed it, it would either collapse or expand indefinitely. Another fascinating, albeit ultimately disproven static model was Macmillan's perpetual motion steady-state universe, which proposed a continuous cycling of matter from light energy to form new stars and galaxies, a cosmic recycling plant that would keep the universe eternally unchanging in its average properties. However, these static visions eventually gave way, pushed aside by accumulating observational evidence, such as the redshifts of galaxies proving expansion, and the inherent theoretical instability of such finely balanced systems, yielding to the dynamic models that now dominate our understanding. Among the earliest and most influential dynamic models, those that truly broke the static paradigm were the de Sitter universe and the Friedman universes. The de Sitter universe, a peculiar but mathematically elegant solution to Einstein's equations, describes an empty, flat universe that expands exponentially, driven solely by the cosmological constant lambda. It is a universe accelerating into an infinite future of ever-increasing emptiness, devoid of matter but full of expansion, a universe that is everywhere but contains nothing. More central to our current understanding are the Friedman universes, which represent a family of solutions where the cosmological constant lambda is initially set to 0, lambda equals 0. These models are rigorously categorized by their intrinsic spatial curvature, denoted by the constant k. K equals 1 describes a closed, spherical universe that is spatially finite, like the surface of a globe, and destined to eventually recollapse in a big crunch. K equals 0 describes a flat, infinite universe that expands forever but asymptotically slows to a halt after an infinite amount of time. And K equals -1 describes an open, hyperbolic universe that is also. These Friedman models, each a distinct cosmic narrative, paint a spectrum of cosmic destinies, ranging from the dramatic bang-bang or closed oscillating scenarios to the eternally expanding whimper of open universes, each with its own beginning and end, or lack thereof. Lemaitre, in his creative exploration of these possibilities, later proposed his own intriguing, quote, hesitation universe, a closed model that included a cosmological constant lambda slightly larger than Einstein's initial value. This led to a period of near-static loitering in its expansion, a kind of cosmic pause where gravity and lambda were almost perfectly balanced, during which galaxies might have had ample time to form and evolve before the universe resumed its expansion towards an eventual recollapse. Similarly, Sir Arthur Eddington conceived of an anti-bang universe, one that began in a delicate, static Einstein state, only to be perturbed by some cosmic fluctuation, causing it to embark on a journey of eternal expansion, a slow unraveling rather than a violent birth. These myriad models, each a distinct cosmic narrative, are systematically classified not only by their intrinsic geometry, the value of K, and its profound implications for the universe's overall shape and curvature, but also by their kinematics, the entire history of their expansion or contraction, from the initial bang to a potential whimper or recollapse, and by their dynamics, the intricate interplay of matter density, radiation density, and the cosmological constant lambda which dictate. These classifications allow cosmologists to explore a vast parameter space of possible cosmic histories, mapping out the theoretical landscape of universes, each a potential cosmic story, each unfolding according to its own internal logic. Intriguingly, cosmologists have discovered that universes in compression, meaning those dominated by radiation in their very early stages, such as the first few tens of thousands of years after the Big Bang, exhibit a higher effective pressure, P equals rho c squared / 3 for radiation. This pressure, perhaps counterintuitively, significantly increases the effective gravitational pull and thus decelerates expansion more effectively and rapidly than matter alone would. It's as if the pressure adds to the gravitational weight of the universe, slowing its outward rush, an extra braking mechanism. Even stranger are universes in tension, which exhibit negative pressure, P equals rush, c squared. This bizarre property, rather than resisting expansion, actually accelerates it, pushing spacetime apart. Such negative pressure can lead to scenarios like constant density, exponential expansion, where the universe grows incredibly rapidly while maintaining a steady density, a phenomenon believed to have occurred during the early universe's dramatic inflationary period, which we will discuss shortly. A profound and persistent challenge in cosmology, one that continues to provoke deep thought, is the homogeneity riddle. Why is the universe so remarkably uniform and isotropic on large scales, appearing almost perfectly smooth in its temperature and matter distribution, even between regions that were causally disconnected in the extremely early universe, having never had a chance to interact and homogenize? How could they have reached such an even temperature and density without any physical communication, any exchange of information? The chaos school of thought suggests that the universe might have begun in a state of extreme disorder, but that some cosmic mechanism, through evolution, smoothed out these irregularities. Models like the Mixmaster universes proposed by Charles Misner explored how chaos could, paradoxically, lead to homogeneity through complex anisotropic contraction and expansion cycles near a singularity, mixing the universe into uniformity through sheer complexity. Conversely, the anti-chaos school argues that such remarkable homogeneity is either a fundamental, initial condition of the universe, inherent from its very beginning, or it is a consequence of the anthropic principle that we observe homogeneity precisely because our existence, requiring a relatively smooth universe for stars and galaxies to form, depends on it. We could not have arisen in a wildly chaotic, lumpy cosmos. Beyond these broad categories of geometry and dynamics, other fascinating theoretical frameworks have been explored. Milne's kinematic relativity, for example, offered a unique perspective, providing a universe that, when translated into the language of general relativity, became an infinite negatively curved universe expanding at a constant rate, continually diluting its matter without ever reaching a singularity, a kind of eternal, lonely expansion. Then there was the highly influential, yet ultimately superseded, continuous creation steady-state universe model, championed by Hermann Bondi, Thomas Gold, and Fred Hoyle in the mid-20th century. This elegant and philosophically appealing model posited a universe that was eternally the same in its large-scale properties, homogeneous, isotropic, and unchanging on average, despite its expansion. To maintain a constant density of matter in an expanding universe, the steady-state theory proposed that new matter was continuously and spontaneously created everywhere in the cosmos, uniformly distributed throughout space, at an imperceptibly slow rate, just enough to replenish the matter diluted by expansion. This model, despite its aesthetic appeal and its elegant simplicity, was ultimately disproven by two monumental discoveries: the detection of the cosmic background radiation in 1964, the definitive afterglow of a hot, dense early universe, and the observation of the evolution of radio sources and quasars, which showed unequivocally that the universe was changing over time, looking different in the distant past than it does today, providing clear evidence for an evolving rather than a steady state. Finally, we consider scalar tensor theories, pioneered by Pascual Jordan and later explored by Hoyle-Narlikar and Brans-Dicke. These theories present a fascinating cosmic dream machine by suggesting that fundamental constants of nature, such as Newton's gravitational constant g or the masses of elementary particles, might not be truly constant, but could, in fact, vary with time or even with position in space. This dynamic variability would mean that the very laws of physics, the rules of the cosmic game, could change over cosmic epochs or across different regions of spacetime, transforming one type of universe into another. While many specific predictions of such theories, such as a measurable variation in g over time, have been disproven by precise observational data, these theories continue to inspire and explore the very flexibility of natural law, pushing the boundaries of what we consider fundamental and immutable about the cosmos. They remind us that our current understanding, while powerful, may still be but one chapter in a much larger cosmic story, a story where even the constants might not be so constant after all. As our minds continue to settle into the gentle rhythm of this cosmic exploration, let's now transition to the actual act of cosmic discovery, the meticulous observations that allow us to decode the universe's grand narrative. It's essential to pause and reflect on the very nature of our knowledge as we do this, for the reader resolved to eschew theory and admit only definite observational facts. All astronomical books are banned. Wise Sir Arthur Eddington once penned, with a twinkle in his philosophical eye, "There are no purely observational facts about the heavenly bodies. Astronomical measurements are, without exception, measurements of phenomena occurring in a terrestrial observatory or station. It is only by theory that they are translated into knowledge of a universe outside." His words resonate deeply, reminding us that even our most direct observations are intrinsically theory-laden, interpreted through the intricate lens of our current scientific understanding and theoretical frameworks. We are always, in a sense, building models and then meticulously testing them against the universe's subtle whispers, its faint signals from across the vastness. It's a continuous dance between hypothesis and evidence. Our profound quest of cosmic decoding begins, perhaps counterintuitively, with local observations, those meticulous measurements made within our own galactic neighborhood and its immediate surroundings. These seemingly mundane, close-to-home measurements form the indispensable foundation upon which all grander cosmic narratives are built, allowing us to accurately calibrate our cosmic rulers. First, the establishment of the, quote, distance ladder is paramount. This intricate series of overlapping methods allows us to measure distances in the universe, step by step, each rung on the ladder building upon the calibration and precision of the previous one, though with accumulating uncertainties as we reach farther out into the cosmos. It begins with the most precise methods for nearby objects, like stellar parallax, the apparent tiny shift in a star's position as Earth orbits the Sun, a direct geometric measurement using simple trigonometry, much like you can estimate distance by closing one eye and then the other. This then extends to standard candles, like Cepheid variable stars, those remarkable pulsating stars whose pulsation periods are directly and reliably related to their intrinsic luminosity, allowing us to infer their distance by comparing their apparent brightness to their known absolute brightness. Further out still, Type Ia supernovae, the cataclysmic explosions of white dwarf stars, provide even more powerful standard candles as they explode with a remarkably consistent peak brightness, allowing us to gauge distances across billions of light-years, reaching deep into cosmic time. Each rung on this ladder is crucial for accurately determining the vast scale of the cosmos, from our backyard to the cosmic horizon, providing a reliable cosmic ruler. Next, we confront one of the most profound and persistent mysteries of modern astrophysics, the enigma of dark matter. Our meticulous observations of galaxy rotation curves, the speeds at which stars orbit the centers of galaxies, reveal a perplexing anomaly. The outer regions of galaxies rotate much faster than predicted by the gravitational pull of their visible, luminous matter alone. This implies that the luminous matter, the stars, gas, and dust we can see with our telescopes, is only a small fraction of a galaxy's total mass. Similarly, analyses of clusters of galaxies show that they move far too fast to be held together solely by the visible matter within them. These clusters would simply fly apart without additional unseen gravity. This missing mass, which does not emit, absorb, or reflect light, and is therefore entirely invisible to our telescopes, dominates the gravitational budget of galaxies and galaxy clusters, posing a profound mystery regarding its composition. It is believed to be mostly non-baryonic, meaning it's not composed of protons and neutrons like ordinary matter, but of some exotic, as yet undiscovered, fundamental particles that interact only weakly with ordinary matter. Its precise nature remains one of the greatest unsolved puzzles in astrophysics, a silent gravitational architect of the cosmos, shaping its structure without revealing its presence directly. Then there are the ages of cosmic objects, which provide critical, independent constraints on the age of the universe itself. The oldest stars, found predominantly in ancient globular clusters, those dense, spherical collections of millions of stars orbiting galactic centers, have estimated ages of approximately 13 to 15 billion years. This, coupled with radioactive dating of the oldest elements found on Earth and in meteorites, which are remnants of the early solar system, sets a firm minimum age for the universe. This age, when combined with the Hubble term h, the current expansion rate, provides crucial checks and balances on various cosmological models, ensuring that the universe is at least old enough for the structures and elements within it to have formed and evolved to their present state, preventing conflicts with our fundamental understanding of stellar and planetary evolution. A powerful diagnostic for the conditions and processes of the very early universe comes from the observed light element abundances. The theory of primordial nucleosynthesis, a cornerstone of the Big Bang model, precisely predicts the formation of the lightest elements, deuterium, heavy hydrogen, helium-3, helium-4, and lithium, in the first few minutes after the Big Bang, when the universe was incredibly hot and dense enough for nuclear reactions to occur, but had cooled sufficiently for nuclei to be stable. The observed cosmic abundances of these light elements today, measured in the most pristine metal-poor regions of the universe, where minimal stellar processing has occurred, are in remarkable agreement with these theoretical predictions, a stunning success of the Big Bang model. This agreement is highly sensitive to the baryon-to-photon ratio, providing a powerful constraint on the amount of ordinary matter in the universe. It tells us that baryonic matter constitutes only about 4 to 5% of the critical density required to make the universe flat, implying that most of the universe's matter is something else entirely, further reinforcing the need for dark matter. Perhaps the most definitive and spectacular piece of evidence for the Big Bang model is the pervasive and uniform cosmic background radiation, CBR. In 1964, Arno Penzias and Robert Wilson, working with a large horn antenna at Bell Labs, serendipitously discovered a pervasive, perfectly thermal microwave background radiation emanating uniformly from all directions in the sky, with a temperature of 2.728 Kelvin. This was, as Dick Peebles, Roll, and Wilkinson at Princeton soon realized, the definitive afterglow of the Big Bang, the relic radiation from a time when the universe was a hot, opaque plasma. Its blackbody spectrum, a perfect Planck curve, is the most perfect ever observed in nature, a stunning confirmation of the hot Big Bang model. Minute anisotropies, or tiny temperature fluctuations, on the order of 1 part in 100,000 in this background radiation, precisely mapped by landmark missions like COBE, WMAP, and Planck, are of paramount importance. These tiny ripples in the early universe's plasma, frozen in time at the epoch of decoupling, are the fossil seeds, the primordial density perturbations, from which all future cosmic structures like galaxies and clusters of galaxies grew through gravitational collapse over billions of years. A larger dipole anisotropy in the CBR also reveals our local motion, the Earth's velocity, through the cosmic rest frame, the average frame of reference of the universe itself, providing a sense of our planet's speed through the grand cosmic flow. Moving beyond our immediate cosmic neighborhood, intermediate distance observations, reaching out to a few 100 million light-years, allow us to map the distribution of galaxies within the local supercluster to which our Milky Way belongs, and beyond. These extensive surveys, like the Sloan Digital Sky Survey, reveal a vast and intricate cosmic web of structures, colossal filaments of galaxies, enormous almost empty voids, and dense superclusters, painting a picture of a universe that is clumpy and hierarchical on scales up to hundreds of millions of light-years. They also reveal systematic peculiar motions, galaxies not only carried along by the Hubble flow but also streaming together, influenced by the immense gravitational pull of these larger structures, hinting at unseen mass that is shaping their movement. The Tully-Fisher relation, an empirical correlation between a spiral galaxy's intrinsic luminosity and its rotation speed, which reliably reflects its total mass, provides a crucial distance indicator for these intermediate scales, allowing us to extend our reach on the cosmic ladder and map the universe in 3 dimensions. Finally, large distance observations, probing billions of light-years away, push our most powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, to the very limits of the observable universe, allowing us to glimpse the cosmos as it was in its infancy. At these immense distances, the simple linear redshift distance law, so useful locally, breaks down, and the intricate effects of cosmological evolution become strikingly apparent. We see that distant galaxies look younger, smaller, more irregular, and often morphologically different from nearby galaxies, reflecting the fact that we are observing them as they were billions of years ago, before they had fully matured into the grand spirals and ellipticals we see today. This necessitates a complex and sophisticated process of mapping observations from the world picture, what we see along our past light cone, a snapshot of different cosmic times, with distant objects appearing younger, onto the world map, the true configuration and distribution of matter in the universe at a single specific cosmic time. It is a challenging task, akin to reconstructing a 3D historical film from a series of evolving 2D images, each representing a different epoch in cosmic history. Despite decades of intense observational effort and theoretical refinement, the precise values of several fundamental cosmological parameters remain the subject of ongoing research and debate, though our error bars continue to shrink, leading us closer to definitive answers. These include h, the Hubble term measuring the current expansion rate, omega, the total density parameter comparing the actual average density of the universe to the critical density required to make it flat, omega b, the baryonic density parameter for ordinary matter, q, the deceleration parameter indicating whether the expansion is accelerating or decelerating, lambda, the cosmological constant or dark energy density, which drives acceleration, and k, the curvature constant determining spatial geometry. The fundamental question: is the universe open or closed? Meaning, is space infinite, flat or hyperbolic, or finite? Spherical. Remains, in a sense, unresolved by direct, definitive observation alone, though our current data strongly points to a flat, open, accelerating universe. However, if we simplify and assume the cosmological constant lambda is 0, which we now know is incorrect, as dark energy exists, then the total density parameter, omega alone, dictates the geometry. If omega greater than 1, the universe is closed and spherical. If omega equals 1, it is flat and infinite. And if omega less than 1, it is open and hyperbolic. Primordial nucleosynthesis, as mentioned, strongly suggests that the baryonic matter density, omega b, is only about 0.04 to 0.05, meaning ordinary matter is far too scarce to curve space into flatness. This implies that if only ordinary matter existed, the universe would be very open, far from flat. This creates a glaring missing matter problem if the universe is indeed flat, omega equals 1, as strongly suggested by inflation theory and the detailed analysis of CBR anisotropies. Such a flat universe would demand vast amounts of dark, non-baryonic matter to make up the difference, adding another layer to the cosmic mystery, a universe dominated by the unseen, by the dark. And so, as the faint echoes of the cosmic background radiation wash over us, let us journey back to the very first moments of existence, to the dawn of everything. The inexorable expansion of the universe, observed today and confirmed by countless pieces of evidence, leads us inevitably and logically to a profound conclusion, that in the distant past, our cosmos must have been in an unimaginably condensed, fiercely hot, and incredibly dense state. This primordial epoch, a time unlike anything we can directly experience, where the very laws of physics were tested to their limits, is what we have come to call the Big Bang. While the term often conjures images of an explosion originating from a central point, it is more accurately understood not as an explosion into something, but rather as the synchronized expansion of all space, everywhere, from an initial ultra-dense state, a state that encompasses all of reality itself, the very beginning of the universe as we know it. The foundations for our modern coherent understanding of the Big Bang were brilliantly laid in the late 1940s by the visionary American physicist George Gamow and his insightful collaborators Ralph Alpher and Robert Herman. They, with remarkable foresight, conceived of a hot early universe, a primordial furnace where light elements could be forged from the fundamental particles. Crucially, their theoretical framework not only described the origin of matter, but also made a startling and ultimately confirmed prediction: the existence of a residual, pervasive thermal radiation, a faint echo of that blazing beginning, which we now know as the cosmic background radiation. Their groundbreaking work, initially overlooked, eventually established the conceptual bedrock for the standard model of the Big Bang, a narrative that continues to be refined and confirmed by an ever-growing body of observational evidence. Let us now embark on a daring journey back in time, a conceptual cosmic safari through the various epochs of our universe's history, glimpsing the profound transformations that shaped it, from the present day back to the very edge of time itself. Our most recent 15 billion years or so, depending on the most current and precise measurements of the Hubble constant and the influence of dark energy, have witnessed the grand sweep of cosmic evolution as we know it. This immense era encompasses the formation and clustering of galaxies, with their intricate spirals, majestic ellipticals, and irregular forms, each containing billions of stars, a dance of cosmic gravity. It spans the birth of our own humble solar system, from a swirling cloud of gas and dust some 4.5 billion years ago, and the long, slow, improbable march of life on Earth, from the simplest single-celled organisms to complex, multicellular creatures, and ultimately to self-aware, intelligent beings capable of pondering their own origins and the universe itself. This is the universe we largely observe and inhabit today, a universe shaped by the laws of physics and the relentless march of time, a universe of stars, galaxies, and life. Venturing further back, we arrive at the first million years of cosmic history, a period of profound transition. At approximately 500,000 years after the Big Bang, corresponding to a redshift of z approximately equals 1,000, the universe had expanded and cooled sufficiently for its temperature to drop to around 3,000 Kelvin, roughly the temperature of the surface of a cool star. This critical moment is known as the decoupling epoch, or recombination. Prior to this, the universe was a superheated, opaque plasma, an ionized soup of free electrons and atomic nuclei, primarily protons and helium nuclei. Photons, light particles, were constantly scattering off these free electrons, unable to travel far without being absorbed and re-emitted, making the universe impenetrable to light, like a thick, glowing fog, a cosmic pea soup. But at decoupling, the temperature dropped to a point where electrons and nuclei could finally combine to form stable, electrically neutral atoms, mostly hydrogen and helium. With the free electrons now bound within atoms, the photons were suddenly no longer scattered. They decoupled from matter and streamed freely across the cosmos, traveling unimpeded through the newly transparent universe, carrying with them a pristine snapshot of the universe at that very moment. This momentous event created the last scattering surface from which the cosmic background radiation originates, the oldest light we can ever hope to see, a direct image of the infant universe, a relic of its fiery youth. This epoch also marks the, quote, epoch of equal densities, a crucial transition where the density of radiation, which decreases rapidly as the universe expands, falling as r to the power of 4 due to both volume dilution and wavelength stretching, finally dropped below the density of matter, which only falls as r cubed due to volume dilution. This transition ushered in the matter era, where the gravitational influence of matter could finally begin to dominate, leading to the gradual clumping of matter and laying the groundwork for galaxy formation, the beginning of structure. Before this, we delve into the radiation era, a period when energy in the form of radiation was the dominant constituent of the universe. This era commenced around 1 second after the Big Bang, at a searing temperature of approximately 10 billion Kelvin, hotter than the core of the Sun. Here, photons were the primary carriers of energy and pressure, constantly interacting with the dense plasma of particles. Crucially, in the very first few hundred seconds of this era, between about 1 second and 3 minutes after the Big Bang, a pivotal nuclear process known as, quote, primordial nucleosynthesis occurred. During this brief, intense window of time, the universe was hot enough for protons and neutrons to fuse together, overcoming their electromagnetic repulsion, forming the first light atomic nuclei, primarily helium-4, accounting for around 25% of all baryonic matter by mass, along with trace amounts of deuterium, a heavy isotope of hydrogen, and lithium. The precise abundances of these light elements observed in the universe today, measured in the most pristine, metal-poor regions of the universe, where minimal stellar processing has occurred, serve as an extraordinary cosmic fingerprint, matching the theoretical predictions of Big Bang nucleosynthesis with remarkable accuracy. This agreement is highly sensitive to the baryon-to-photon ratio, providing a powerful constraint on the amount of ordinary matter in the universe, a beautiful confirmation of the early Big Bang conditions. Even further back, preceding the radiation era in its purest form, we encounter the first second of existence, a time of immense energy and exotic particles, a realm of fundamental forces and nascent matter. This period includes the lepton era, spanning from approximately 10 to the power of 4 seconds to 1 second after the Big Bang, with temperatures ranging from 10 to the power of 12 to 10 to the power of 10 Kelvin. Here, the universe was an incredibly dense and hot soup of fundamental particles, electrons, their antimatter counterparts positrons, heavier leptons like muons, and a vast sea of elusive neutrinos. As the universe continued to expand and cool, a significant event took place, muons being heavier, and then electron-positron pairs annihilated with each other, converting their mass energy into a flood of photons, further heating the cosmos. The elusive neutrinos, interacting only very weakly with other matter, decoupled from the rest of the cosmic plasma even earlier, at around 1 second. They now stream freely through the universe, almost entirely undetected, forming a faint, almost imperceptible cosmic neutrino background, a ghost from the universe's first moments, carrying information about an even earlier, hotter epoch, a relic as ancient as the CBR. Pushing the boundaries of our knowledge still further, we arrive at the first 100 microseconds, specifically before about 10 to the power of 7 seconds after the Big Bang, when temperatures soared above an unimaginable 10 to the power of 13 Kelvin. This was the Hadron era, a turbulent and incredibly dense realm where strongly interacting particles like protons, neutrons, and pions, along with their antimatter counterparts, constantly annihilated and were recreated from the incredibly energetic plasma, a maelstrom of fundamental particles. A profound and still mysterious event occurred within this era, the slight matter-antimatter asymmetry. For reasons still not fully understood, but involving fundamental physics processes, a mechanism known as abiogenesis, there was a tiny, minuscule excess of matter over antimatter, perhaps just 1 part in a billion. This tiny imbalance, a cosmic stroke of luck, meant that after the widespread annihilation of matter and antimatter, a small residue of matter survived, forming all the baryonic matter, the protons and neutrons, that constitutes everything we see today: stars, galaxies, planets, and ourselves. Before this, at even higher energies and temperatures, the hadrons themselves dissolved into their fundamental constituents, the elementary quarks and leptons. It was also during these unimaginably energetic first moments that the 4 fundamental forces of nature, the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity, which we observe as distinct today, gradually separated or froze out from an initial unified superforce that governed the universe at these extreme energies, much like water freezing from a single liquid phase into distinct ice crystals as it cools. And finally, we reach the very edge of our theoretical understanding, the realm of speculative physics, the domain of quantum gravity, beyond 10 cubed to the power of 6 seconds, at temperatures exceeding 10 to the power of 28 Kelvin, corresponding to particle energies of 10 to the power of 15 giga-electron volts, we enter the hypothetical grand unified era. Here, according to grand unified theories, GUTS, the electroweak force, the unified electromagnetic and weak forces, and the strong nuclear force are theorized to unite into a single, more fundamental hyperweak force, revealing a deeper symmetry in nature, a cosmic elegance. This era, and the even earlier truly primordial Planck epoch, at 10 to the power of 4 to the power of 4 seconds after the Big Bang, with densities of 10 to the power of 94 grams per cc, temperatures of 10 to the power of 32 Kelvin, and particle energies of 10 to the power of 19 giga-electron volts, represents the absolute frontier of our current understanding. In this epoch, the very fabric of spacetime is theorized to be dominated by quantum fluctuations, becoming a chaotic, frothing spacetime foam where quantum effects on gravity are paramount. This is where classical general relativity breaks down, and we enter the tantalizing, speculative realm of quantum cosmology, where entirely new physical laws may govern the very beginning of the universe, and indeed where the concepts of space and time as we know them might not even apply, a realm beyond our current grasp. And so, as the profound narrative of the early universe fades into these ultimate theoretical horizons, we are brought face to face with the very limits of our cosmic perception, Our view of the cosmos is not, in fact, boundless, as it might appear on a clear, starry night. We are fundamentally constrained by invisible boundaries, by profound conceptual limits known as cosmological horizons. These are not physical walls or edges, like the fence around a garden, but rather limits on what we can observe, what we can know, and what we can ever interact with, imposed by the finite speed of light and the finite age and expansion history of our universe. They define the very scope of our cosmic understanding, delineating the knowable from the unknowable, the observable from the forever hidden. One such crucial boundary is the, quote, particle horizon. This horizon marks the maximum distance from which light, or any other form of information, could have reached us since the very beginning of the universe, or since the earliest causally connected moment, such as the Big Bang. It is the boundary in space beyond which the world lines of galaxies or particles have not yet, and indeed could not have, intersected our past light cone. It delineates the observable universe from the unobservable universe, the known from the perpetually unknowable. As the universe ages and light from ever more distant regions has had more time to reach us, this particle horizon continuously expands at the speed of light, constantly revealing new vistas of the cosmos. With each passing moment, a tiny sliver more of the previously unobservable universe swims into view, a silent, perpetual unveiling of cosmic history, like the ever-expanding circle of light from a lighthouse. A second, conceptually distinct and often more challenging horizon to grasp is the event horizon. Unlike the particle horizon, which defines what we have observed or could have observed up to the present moment, an event horizon is a boundary in spacetime beyond which events, brief happenings in a particular location and time, can never be observed by a particular observer, even if that observer were to wait for an infinite amount of time. It is defined by the observer's ultimate light cone in the infinite future, or, conversely, the ultimate light cone in the infinite past. For instance, in a universe that continues to accelerate its expansion forever, due to dark energy, galaxies beyond a certain distance will eventually recede so fast that their light will never reach us, even if we waited for eternity. Those galaxies lie beyond our future event horizon, their light eternally trapped by the expanding space between us, their future signals forever out of reach. In a hypothetical, perfectly static universe of finite age, a particle horizon would still exist, simply because light has only had a finite amount of time to travel since the universe's beginning. However, an event horizon would only exist in such a static universe if it also had a finite future, if, for instance, all light sources were destined to burn out or cease shining at some point. The concept of event horizons becomes particularly salient in specific cosmological models, such as the de Sitter universe, an empty universe that accelerates exponentially, or the now disproven steady-state universe, which imply an infinite past from which light could always have reached any point, but a limited future observability, as light from ever more distant regions eventually gets redshifted beyond detectability, or simply never reaches us, leaving part of the future forever hidden. A deep intellectual puzzle known as the horizon riddle asks, can information from beyond a particle horizon ever be communicated or known by another observer within our observable universe? The answer, dictated by the immutable speed of light, is a definitive no. Because the speed of light is the ultimate cosmic speed limit for all communication and interaction, no signal can travel faster than light, and therefore no information can cross a particle horizon from the unobservable side to the observable side. This inherent limitation defines the causal structure of our universe, placing fundamental boundaries on what we can ever truly know about the cosmos. This leads us directly to the more specific and famous horizon problem within the standard Big Bang model. A a profound paradox that long troubled cosmologists until the advent of inflation theory. The problem arises from the remarkable observation that regions of the cosmic background radiation, now visible to us on opposite sides of the sky, appear to be in virtually identical thermal states, exhibiting almost precisely the same temperature and smoothness, despite being separated by vast distances. Yet at the time of decoupling, when the CBR was emitted, some 380,000 years after the Big Bang, these regions were so far apart that they were causally disconnected. They lay outside each other's particle horizons, meaning they never had time to exchange energy or information. How, then, could they have achieved such an astonishing degree of uniformity and thermal equilibrium without any physical interaction? It was a perplexing challenge to the coherence and completeness of the Big Bang model, a glaring flaw that demanded explanation. Another significant cosmic boundary is the Hubble sphere. This is the region of space surrounding any observer within which galaxies are observed to recede at less than the speed of light. V less than c. Galaxies outside this Hubble sphere, by definition, recede from us at superluminal speeds, v greater than c, that is, faster than the speed of light. Again, it is critical to reiterate that this does not violate Einstein's special relativity, as special relativity governs the motion of objects through space, not the expansion of space itself. The space between us and these distant galaxies is simply stretching so rapidly that the galaxies are carried away faster than light can traverse the expanding distance, an effect of the stretching metric. The boundary of the Hubble sphere, where v equals c, is sometimes referred to as the, quote, photon horizon. This is conceptually akin to the country of the Red Queen, a whimsical yet accurate reference to Lewis Carroll's Through the Looking Glass, where the Red Queen tells Alice, "It takes all the running you can do to keep in the same place." Here, at the photon horizon, light emitted towards us from this boundary would, in effect, appear to stand still relative to us, constantly being carried away by the expanding space as quickly as it tries to approach, making no headway. In a universe that is decelerating, its expansion slowing down, the Hubble sphere actually expands faster than the galaxies within it. This means that galaxies initially receding superluminally can eventually fall into our Hubble sphere, and the light they emitted at that superluminal distance, which was initially being carried away from us faster than it could travel, will eventually catch up and begin to approach us, allowing us to finally observe them. This is a subtle but important detail for understanding the full observational scope of the universe's past and what we might someday see. To simplify the visualization of these complex space-time geometries and horizons in complex expanding universes, cosmologists often employ conformal diagrams, also known as Penrose diagrams. These ingenious diagrams compress the infinite extent of space and time into a finite plot using a special coordinate transformation. This allows world lines, the paths of objects through space-time, to appear parallel, and light cones, the paths of light, to appear straight, irrespective of the underlying space-time curvature. This enables a much clearer visualization of the causal structure and the precise placement of various horizons, making complex relativistic scenarios more accessible to the human mind. Universes that possess a definite beginning in conformal time, a transformed time coordinate, will necessarily have particle horizons, defining the limits of what can be observed from their past. Conversely, universes that have an end in conformal time will exhibit event horizons, defining the limits of what can ever be observed in their future. Critically, fascinating theoretical models like the de Sitter universe, which accelerates exponentially, and the now disproven steady-state universe, have event horizons, but no particle horizons. This implies an infinite past, from which light could always have reached any point, but a limited future observability, as an accelerating expansion, ensures that increasingly distant events become permanently unobservable. The universe can present us with an ever-receding horizon, an ultimate limit to our knowledge, eternally withholding its furthest secrets, a cosmic veil drawn across the deepest mysteries, inviting us to wonder what lies beyond. And so, as we contemplate these profound cosmic limits, these horizons of perception and knowledge, our journey now takes us to one of the most elegant, audacious, and profoundly successful ideas to emerge in theoretical cosmology in recent decades: the concept of inflation. This revolutionary theoretical framework, still under active development and refinement, dramatically reimagined the very earliest moments of the Big Bang, offering compelling and satisfying solutions to several long-standing puzzles that had vexed cosmologists for decades, threatening to unravel the elegant simplicity of the Standard Model. It begins by positing an initial state of perfect symmetry at unimaginably extreme energies, specifically during the hypothetical grand unified era, around a fleeting 10, cubed to the power of 6 seconds after the Big Bang, when the universe's temperature was a staggering 10 to the power of 28 Kelvin. In this ultra-hot, ultra-dense primordial soup, the fundamental forces of nature, the strong nuclear force, the weak nuclear force, and the electromagnetic force, are theorized to have been unified into a single, more fundamental, grand unified force, a beautiful display of underlying cosmic unity, a single principle governing all. During this extraordinary epoch, the prevailing grand unified theories, gut, which seek to describe this unified force, made a specific and deeply problematic prediction: the copious creation of exotic, stable, and incredibly massive particles known as magnetic monopoles. These would be isolated north or south magnetic poles, unlike the familiar magnets we know, which always have both poles bound together. If the universe had evolved normally, according to the standard Big Bang model without inflation, these monopoles would have been overwhelmingly abundant today, a veritable sea of them, leaving a clear and unmistakable observational signature. However, despite extensive and dedicated searches using various detection methods, no such magnetic monopoles have ever been definitively detected. This stark contradiction between theory and observation presented a significant hurdle, a major embarrassment for the Standard Model, famously known as the, quote, monopole problem. It was Alan Guth, a brilliant American physicist, who in 1981 boldly proposed a radical solution to these cosmic conundrums. He suggested that the grand unified phase transition, the moment when the unified force broke into the distinct strong and electroweak forces, akin to water freezing into ice, releasing latent heat, did not happen abruptly or uniformly throughout the nascent universe. Instead, the universe supercooled, much like highly pure water, can remain liquid below its freezing point in the absence of nucleation sites. It entered a fleeting but profoundly significant state of false vacuum. This false vacuum was not truly empty. Rather, it was permeated by an immense intrinsic energy density, a kind of inherent tension in space-time itself, like a coiled spring of cosmic proportions. Crucially, this false vacuum possessed an extraordinary and counterintuitive property: immense, negative pressure equivalent to a cosmic tension. P equals rho c squared, where P is pressure, rho is energy density, and c is the speed of light. This bizarre negative pressure, unlike ordinary pressure that acts to slow down expansion, actually generates a powerful repulsive gravitational effect, causing the universe to expand exponentially and accelerate at an astonishing rate. This brief, incredibly rapid expansion, lasting for an unimaginably tiny fraction of a second, perhaps from 10 cubed to the power of 6 to 10 cubed to the power of 4 seconds after the Big Bang, is what we call inflation. During this infinitesimal interval, the universe expanded by a staggering factor, perhaps 10 to the power of 26 or even more, growing from subatomic scales to macroscopic or even astronomical sizes almost instantaneously, faster than light could traverse any existing space. Inflation, in its elegant sweep, offered compelling solutions to several profound cosmological puzzles. It solves the monopole problem by effectively diluting these troublesome particles to an unobservably low density. Imagine if you had a single monopole in a small volume, and then that volume expanded by a factor of 10 to the power of 26. The chances of finding that monopole become astronomically, microscopically small, rendering them effectively non-existent in our observable universe. It also offers a powerful and elegant solution to the flatness problem. Why is the universe observed today to be so incredibly close to the critical density, omega equals 1, meaning its spatial geometry is remarkably flat on large scales? Without inflation, achieving such flatness would require an incredibly precise, almost miraculous, fine-tuned initial condition for the universe's density at the Big Bang, deviating by no more than 1 part in 10 to the power of 50. Inflation elegantly resolves this by stretching any initial curvature, no matter how extreme, to negligible levels, much like inflating a wrinkled balloon until its surface appears perfectly smooth and flat to any observer on its surface. Any initial bumps or curves are simply stretched far beyond the observable horizon, effectively making our observable universe appear flat. Furthermore, inflation provides a powerful and satisfying answer to the aforementioned horizon problem. The paradox of widely separated regions of the cosmic background radiation appearing in thermal equilibrium, exhibiting almost precisely the same temperature and smoothness despite being causally disconnected at the time of decoupling, having never had time to interact, is beautifully resolved. Before inflation, these regions were, in fact, part of a tiny, causally connected patch of the universe, small enough for heat and information to diffuse and homogenize. Inflation then rapidly stretched this once small, homogeneous region to a size vastly exceeding the current observable universe, ensuring that the distant regions we now see were indeed once in causal contact and thermal equilibrium, having exchanged energy and homogenized their temperatures. At the end of the inflationary epoch, the immense latent energy stored in the false vacuum is suddenly released, like a phase transition, rapidly reheating the universe and filling it with a hot, dense plasma of quarks, leptons, and gluons, thereby seamlessly initiating the standard Big Bang evolution that follows. Picking up where the traditional Big Bang model began, but with its initial conditions perfectly set by this earlier, rapid expansion. The observed density of dark matter far exceeding that of luminous baryonic matter, with omega B approximately equals 0.05 from nucleosynthesis. Yet the strong observational evidence from CBR anisotropies and large-scale structure, suggesting omega is close to 1 as predicted by inflation, points strongly to the existence of vast amounts of dark non-baryonic matter. This missing matter is not made of protons and neutrons but of exotic, as yet undiscovered particles, such as massive neutrinos or hypothetical WIMPs, weakly interacting massive particles. These forms of matter are not only crucial for accounting for the universe's overall mass budget, but are also fundamental to our current models of galaxy formation. Inflation, in its elegant tapestry, also provides the primordial seeds for these structures. Tiny quantum fluctuations in the vacuum, inherent to quantum mechanics, are stretched by the exponential expansion of inflation into macroscopic density perturbations. These slight overdensities and underdensities then grow over billions of years through gravitational instability, forming the intricate cosmic web of galaxies, galaxy clusters, and superclusters that we observe today. Thus, inflation beautifully links the quantum world of the very small to the cosmic structure of the very large, explaining the origin of cosmic structure from fundamental quantum jitters, a cosmic blueprint laid down in the earliest moments. And so, as we continue our gentle exploration, allowing these profound concepts to settle in our minds, let us now consider a fascinating and often perplexing aspect that emerges when we measure the fundamental properties of the universe, not in arbitrary human units, but in its own intrinsic natural units. These are scales derived from the most fundamental constants of nature, such as the mass of the nucleon, proton/neutron, the Planck length, the smallest theoretically meaningful length scale, or the speed of light. When we do this, a curious pattern of numbers reveals itself, a cosmic numerology that has deeply intrigued and perplexed scientists for generations, hinting at a hidden order or a profound coincidence beneath the surface of reality. We find, for instance, a unity group of small, dimensionless numbers, ratios of fundamental constants that seem almost arbitrarily precise, yet are profoundly important for the very existence of matter and life. Consider the nucleon to electron mass ratio, Mn/me, which is approximately 1836, or the fine structure constant, alpha, roughly 1/137th, which governs the strength of electromagnetic interactions and determines, for example, how strongly electrons are bound to atomic nuclei, ultimately dictating the stability of atoms. These numbers, seemingly plucked from a cosmic lottery, are profoundly important for the existence of stable atoms, the complexity of chemistry, and the formation of stars. Yet their specific values are not derivable from first principles. They simply are, as far as we know, fundamental givens. But then, an even more striking and mysterious pattern emerges with the, quote, large numbers. These are vast, dimensionless quantities, colossal in scale, clustered mysteriously around the immense value of 10 to the power of 40. For instance, the ratio of the electrical force to the gravitational force between a proton and an electron, E² gmnme, is an astonishing 10 to the power of 40, highlighting the immense weakness of gravity compared to electromagnetism. Similarly, the ratio of the universe's current age measured in fundamental atomic time units, e.g., the time it takes light to cross a proton or the lifetime of an electron, also hovers around this same colossal value, approximately 10 to the power of 40. This remarkable cosmic connection, where seemingly disparate large numbers, n approximately equals n, one representing a ratio of fundamental forces, the other reflecting the current state of the universe, its age or size, appear to be approximately equal, led the brilliant British physicist Paul Dirac to propose his audacious large number hypothesis in 1937. He posited that these large dimensionless numbers are not merely coincidental but are fundamentally related, suggesting a deeper, underlying physical connection that demands explanation, implying a cosmic design or a dynamic interplay between fundamental constants and cosmic evolution. This striking correlation, however, immediately poses a cosmic number problem. While n, the ratio of fundamental forces, appears to be a fixed constant, n, a number reflecting the size or age of the universe, is clearly not. The universe is continuously expanding, and its age is continuously increasing. If these numbers are fundamentally linked, and n is changing, then n must also be changing, or their observed equality is merely a transient, fleeting coincidence that only holds true for a particular epoch. Dirac's bold and controversial solution to this problem was to propose that n and n were permanently related throughout cosmic history, meaning that the gravitational constant g itself must slowly decrease over cosmic time, subtly weakening its pull as the universe aged. This was a radical suggestion, implying that the very strength of gravity was not a fixed constant but a dynamic parameter, challenging one of the supposed cornerstones of physics. However, precise astronomical observations, particularly of the orbital periods of planets, the dynamics of binary pulsars, and geological evidence from Earth, have provided stringent constraints, essentially disproving the hypothesis that G varies significantly over cosmic timescales. Other proposed solutions to the cosmic number problem have emerged, seeking to explain this peculiar numerical alignment. Sir Arthur Eddington, for example, sought to link these large numbers to the cosmological constant and other fundamental physical parameters, suggesting a profound relationship between the universe's expansion and the fundamental forces, perhaps arising from a unified theory. Perhaps the most widely discussed and often controversial explanation involves an appeal to the anthropic principle, particularly its weak form, championed by the American physicist Robert Dicke. This principle argues that the observed values of fundamental constants, including these large numbers, are not necessarily unique or fundamentally derived from some ultimate theory. Rather, we observe them to be within the life-permitting range precisely because we can only exist in such a universe. If the constants were different, if the universe were inhospitable to stars, elements, and planets, there would be no observers to witness it. This implies a vast ensemble, a multiverse, of other universes, each with different constants, the vast majority of which are lifeless and therefore unobserved. We simply happen to find ourselves in one of the rare, life-permitting universes where these numbers naturally coincide during our epoch. The coincidence in this view is a selection effect, not a fundamental law, our existence shaping our observation. And so, as the cosmic numbers hint at deeper connections, and perhaps even our own observational biases, let's now consider a seemingly simple, yet profoundly vexing question that has perplexed thinkers for centuries, a question that, when fully understood, reveals deep truths about our universe's evolution. This query, why is the sky dark at night, universally known as Olbers' paradox, after the German astronomer Heinrich Wilhelm Olbers, who famously articulated it in 1823, though it had been discussed by others, including Kepler and Halley centuries earlier, highlights a deep conflict between our intuitive expectations about an infinite, eternal universe and the stark, serene reality of our nocturnal observations. If the universe were truly infinite in spatial extent, uniformly filled with an eternal distribution of luminous stars, then, logically, every single line of sight from Earth, in whatever direction we might look, should eventually terminate on the surface of a star. This would, by all accounts, render the entire night sky as blindingly bright as the surface of our sun, a cosmic blaze utterly contrary to the familiar and comforting darkness we experience after dusk. It would be a universe without night, a perpetually bright and searing inferno. Early attempts to resolve this unsettling paradox proposed various solutions, each reflecting the scientific understanding of its time. Johannes Kepler, in the 17th century, grappling with a finite universe, suggested that the universe was bounded by a cosmic wall beyond which there were no stars, thus limiting the incoming light. Later, in the 18th and 19th centuries, thinkers like Jean-Philippe Deschamps and Olbers himself proposed that vast amounts of interstellar dust and gas might absorb the light from distant stars, thus dimming the sky to explain its darkness. However, the brilliant astronomer John Herschel pointed out a fatal flaw in this absorption theory. If the dust were indeed absorbing light from an infinite array of stars, it would inevitably heat up over time until it glowed with the same intensity as the stars themselves, radiating energy and thus failing to solve the paradox. The energy would simply be re-emitted, perhaps at different wavelengths, but the night sky would still be bright, just with a different spectrum. Other complex solutions involving hierarchical clustering of matter, where stars grouped into clusters, clusters into superclusters and so on, in an infinite fractal pattern, were also suggested, hypothesizing that there were simply fewer stars at greater distances, but these models too ultimately proved insufficient to account for the pervasive darkness. The problem required a more fundamental insight, the definitive resolution to Olbers' paradox, a solution both elegant and profound, quantitatively provided by Lord Kelvin in 1901 and poetically anticipated by the American writer Edgar Allan Poe in his philosophical prose poem Eureka, 1848, lies not primarily in the spatial distribution of stars, but in the fundamental properties of time and light in our universe, specifically the finite stellar lifetimes and the finite speed of light. The sheer, unfathomable scale of the cosmos means that the lookout limit, the average distance one can see along a line of sight before it actually hits the surface of a star, is astronomically vast, far exceeding distances measurable in our local galaxy. But stars, like our own sun, do not shine forever. They have finite luminous lifetimes, typically about 10 billion years for sun-like stars. More importantly, and most critically, the universe itself has a finite age, roughly 13.8 billion years since the Big Bang. This means we simply haven't had enough time for light from stars beyond a certain cosmic distance, roughly 13.8 billion light-years, adjusted for the effects of cosmic expansion, to have reached us. Thus, the sky is dark, not because stars are invisible or missing from the distant universe, but because starlight from sufficiently distant stars is too feeble, or, more accurately, has not yet had enough time to arrive and fill the dark universe. The universe is not old enough for distant light to have propagated across its entire expanse, and individual stars do not shine long enough to illuminate the entire cosmos from every direction, even if the universe were infinite in extent. We are seeing a universe that is both spatially and temporally vast, but ultimately finite in age. While the expansion of the universe does contribute to the darkness by causing the light from distant galaxies to be redshifted, shifting visible light into the infrared or microwave spectrum and thereby reducing its apparent intensity and energy, this effect alone only slightly reduces the total amount of light and does not, by itself, fundamentally solve the paradox. It dims the light but doesn't eliminate it entirely. The primary reason for the dark night sky remains the finite age of the universe and the finite luminous lifetimes of stars. So, the night sky is not, in fact, truly empty or dark. It is covered, but not by the visible light of stars. It is covered, bathed in a uniform, ethereal glow by the highly redshifted, faint but omnipresent cosmic background radiation. The cooling, fading afterglow of the Big Bang itself, pushed into the microwave spectrum by billions of years of cosmic expansion. This ancient light, the very first light freed from the early universe's opaque plasma, provides a deeper, more profound and elegant answer to Olbers' paradox than anyone could have imagined centuries ago, connecting the darkness of our night to the brilliance of the universe's dawn, a cosmic lullaby from the earliest times. As we gently drift from the gentle glow of the cosmic background radiation, we are inexorably led to the deepest, most profound questions humanity has ever dared to ask. Questions that touch upon the very nature of existence itself, of beginnings and endings. These are the intertwined realms of cosmogenesis, the ultimate origin of the universe itself, cosmogony, its infancy and early evolution, eschatology, its final stages, its ultimate destiny, and cosmothanatology, its ultimate death. These are not merely scientific inquiries, coldly detached, but deeply interconnected philosophical and existential questions that resonate with our inherent human need for narrative and meaning, for understanding the story of everything. Across cultures and throughout history, ancient creation myths arose, serving to provide narrative meaning, a sense of cosmic order, and a framework for understanding bewildering existence. Sumerian, Egyptian, and Indian cultures often conceived of vast, cyclic universes, eternally expanding and contracting, a cosmic breath of Brahman, a continuous cycle of destruction and renewal, a dance of creation and dissolution. Stoic and Mayan philosophies also embraced cyclical time, with periodic destruction and renewal of the cosmos. Chinese and Greek cosmogonies, too, wrestled with the origins of order from primordial chaos, often invoking primordial beings or forces, deities, or the spontaneous arising of patterns from the formless void. While these myths provided powerful cultural narratives, shaping worldview and morality, they invariably left the question of their own origin unanswered. From whence did the primordial waters or the creator deity arise? What was before the beginning of their story? The Mosaic chronology, based on a literal interpretation of biblical texts, famously posited a universe created a mere few thousand years ago. This timeline, however, was dramatically overturned by the irrefutable evidence accumulated by geology, with its vast timescales of rock formation and fossil records, and astronomy, with its observations of immense cosmic distances and stellar evolution in the 18th and 19th centuries, revealing a vastly, unimaginably older Earth and cosmos, demanding a new narrative. Philip Gauss's notorious book, Omphalos, An Attempt to Untie the Geological Knot, 1857, which controversially proposed a universe created by God with a fictitious ancient history, e.g., Adam having a navel, fossils already in rocks, light already on its way from distant stars, vividly highlights the inherent tension and conflict that can arise between literal religious faith and the relentless march of scientific inquiry that seeks evidence-based explanations for the modern cosmology, building upon the robust framework of the Big Bang, has fundamentally transformed our approach to cosmogenesis. It views the universe's origin not as an event in space or in time, as if the universe were born within some pre-existing container or clockwork mechanism. Rather, it conceptualizes cosmogenesis as the timeless, spaceless creation of space and time themselves. The Big Bang, in this refined understanding, is not an explosion into something, but the earliest moment within our universe's time. The singularity where our known physical laws break down. It is not its creation by some external agent acting from outside space and time, but the very boundary of our space-time continuum, the point beyond which our current physics cannot penetrate. The problem of how the universe began is thus transformed from a narrative of creation in the universe, as, for example, the continuous creation of matter in the now disproven steady-state theory, which posited creation within an existing framework, to one of creation of the universe. A far more profound and challenging question concerning the very genesis of physical reality, the inception of existence itself. This applies equally to all types of universes, whether they are finite or infinite in extent or duration, as they all grapple with the concept of a fundamental beginning. The question of the fitness of the universe, why its fundamental constants and initial conditions appear to be so precisely tuned, so exquisitely balanced, for the emergence of complex structures, and, ultimately, for life itself, is a distinct but deeply related and highly debated topic. This fine-tuning problem has led to several possible interpretations. Theistic theories posit intentional design by a supreme, intelligent being, a cosmic architect who crafted the laws and constants for a specific purpose, such as the emergence of life and consciousness. Anthropic theories in their various forms offer a scientific counterpoint. The weak anthropic principle, championed by the American physicist Robert Dicke, argues that the observed values of fundamental constants, including the precise parameters that allow for carbon-based life, nuclear fusion in stars, and stable planetary orbits, are not necessarily unique or fundamentally derived from some ultimate theory. Rather, we observe them to be within the life-permitting range, precisely because we can only exist in such a universe. If the constants were different, if the universe were inhospitable to stars, elements, and planets, there would be no observers to witness it. This implies a vast ensemble, a multiverse, of other universes, each with different constants, the vast majority of which are lifeless and therefore unobserved. We simply happen to find ourselves in one of the rare, life-permitting universes where these numbers naturally coincide during our epoch. The coincidence, in this view, is a selection effect, not a fundamental law, our existence shaping our observation. More speculative still are spontaneous creation theories, which propose that universes can, in principle, self-create from nothing, meaning from a quantum vacuum, or from quantum fluctuations in some larger meta-universe, perhaps generating baby universes, or bubbles of new spacetime that bud off from existing ones, a continuous process of cosmic genesis and proliferation, a universe birthing itself. This frames creation not as a singular miracle, but as a statistical possibility inherent in the laws of quantum mechanics, a universe arising from the very fabric of quantum foam. Most provocatively, and pushing the boundaries of scientific imagination, are natural selection theories of universes. Lee Smolin, for example, has proposed a model of cosmological natural selection, sometimes called the fecund universes theory. This theory suggests that universes might reproduce, e.g., through black hole singularities, which could act as birth canals for new universes, passing on slight genetic variations in their fundamental constants to their offspring, much like biological evolution. Universes that are most fertile for black hole formation, which in turn implies the existence of stars, planets, and possibly life as a byproduct of the conditions that favor black holes, would then become most abundant in a larger ensemble of multiverses. In an even more speculative vein, it has been proposed that highly advanced intelligent life in parent universes might actively engage in the creation of offspring universes, perhaps through quantum engineering or manipulating spacetime, selecting for fitness and thereby perpetuating intelligence itself across cosmic generations, making intelligent life not just a product, but a potential creator of universes. Alan Guth, the pioneer of inflation, has even discussed the theoretical possibility, albeit far in the future, of creating a universe in a laboratory, a thought experiment that blurs the line between creation and scientific endeavor, pushing the limits of what we define as natural, and indeed what we define as creator. Now, having contemplated the universe's beginning and its potential modes of genesis, let us turn our gaze to its ultimate end, to the cosmic finale, eschatology. In approximately 4 to 5 billion years, our sun will exhaust its core hydrogen, swell into a red giant, expanding so dramatically that it will engulf Mercury and Venus, and eventually make Earth uninhabitable, its oceans boiling away. Life on our planet will perish long before this, a local end to our story. But what of the cosmos as a whole, the fate of the universe beyond our solar system, beyond our galaxy? The universe, based on its geometry and dynamics, faces two broad, grand possibilities for its ultimate fate, two distinct cosmic destinies, each with its own profound implications. 1. The Big Bang returns, the Big Crunch. If the universe is a closed universe, meaning its total energy density omega greater than 1, or in the presence of dark energy, if the cosmic expansion eventually turns around and recollapses, its expansion will eventually cease, halt, and then reverse. Gravity, triumphant and relentless, will pull all matter back together, causing the universe to contract into a final, fiery singularity, a reverse Big Bang, often poetically termed the Big Crunch. This Bang Bang, or oscillating universe model, where the universe undergoes an infinite series of expansions and contractions, was once a popular and elegant idea, suggesting a cyclical cosmos without a true beginning or end, a cosmic heartbeat. However, thermodynamic arguments, particularly the relentless, irreversible increase of entropy with each cycle, suggest that each new cycle would be larger, hotter, and progressively more disordered than the last, ultimately leading to uninhabitable bright sky starless cycles or hot death scenarios, where the universe becomes too hot and full of radiation to allow for the formation of stars or any complex structures capable of supporting life. The universe might simply expand to a certain point, then contract, only to rebound into a new cycle, but without fully resetting its entropy, accumulating disorder with each iteration. 2. Eternal darkness and emptiness, the big freeze/heat death. Conversely, if the universe is an open universe, meaning its total energy density omega less than 1, or a flat universe, omega equals 1, dominated by a cosmological constant, dark energy, that drives accelerated expansion, which is what current observations strongly suggest, it will expand forever. This is the scenario currently favored by observational evidence, a chilling prospect of endless dilution and increasing emptiness. In this bleak, distant future, galaxies will drift ever farther apart, eventually becoming isolated islands in a vast, empty, and increasingly cold cosmos, beyond the reach of each other's light. Their stars will exhaust their fuel, grow dark, and die, eventually forming stellar remnants like white dwarfs, neutron stars, and black holes. Over unimaginably vast timescales, stellar systems will evaporate, their planets flung into the void. The black holes themselves will slowly merge into supermassive black holes, and even these ultimate gravitational devourers will eventually evaporate via Hawking radiation, a process taking 10 to the power of 66 years for a stellar mass black hole, and up to 10 to the power of 100 years for a supermassive one, transforming their mass into a diffuse, faint glow of photons and elementary particles. Even protons themselves, the stable building blocks of ordinary matter, might eventually decay, on timescales estimated around 10 to the power of 35 years or more, depending on theories of grand unification, reducing all remaining matter to an extraordinarily dilute cold soup of photons, neutrinos, and electrons, spreading ever thinner into an eternity of near absolute zero temperature. This is the big freeze or heat death of the universe, a silent, solitary, and ultimately featureless end, where all energy is uniformly distributed, and no further work can be done, no further change can occur. A more extreme version, if dark energy's repulsive force continues to strengthen and dominate, is the theoretical Big Rip, where the accelerating expansion becomes so violent that galaxies, stars, planets, and even atoms themselves are eventually torn apart, ending in a catastrophic dissolution of all structure, a universe ripped into its most fundamental constituents. Sic transit gloria mundi, thus passes the glory of the world. a poignant epitaph for a universe destined for an endless, cold, and empty night, a final, quiet slumber. And now, as our cosmic journey approaches its peaceful conclusion, having navigated the vastness from its origin to its ultimate destiny, let us bring our contemplation closest to home, to the most exquisite and improbable phenomenon within this vast, impersonal cosmos, life itself. The question of how life originated on Earth has been a subject of intense philosophical and scientific debate for millennia, deeply interwoven with our sense of purpose and uniqueness in the grand scheme of things. Special creation theories, invoking supernatural acts of a divine being, offered comfort and meaning to many, positing life as a unique, intentional gift directly implanted or breathed into existence. However, the relentless progress of chemistry and biology began to challenge these views, demonstrating that organic molecules, the very building blocks of life such as amino acids, sugars, and nucleic acid bases, can be readily formed from inorganic precursors under conditions thought to have existed on the early Earth. This opened the door to natural, rather than solely supernatural, explanations for abiogenesis, the origin of life from non-living matter. Early spontaneous creation theories, prevalent from ancient Greece through to the medieval period, suggested that life could spontaneously arise from inanimate matter, e.g., Aristotle's belief that worms arose from decaying flesh, or the popular notion that maggots spontaneously generated in meat, or mice from dirty rags. While these specific instances were famously disproven by Louis Pasteur's elegant experiments in the 19th century, which showed that life only arises from pre-existing life, biogenesis, they highlight the enduring mystery and the human desire to understand abiogenesis, the actual origin of life from non-living components, a process that must have happened at least once. Panspermia theories, championed by scientists like Svante Arrhenius in the early 20th century, and later re-examined by luminaries like Francis Crick, co-discoverer of DNA structure, and Leslie Orgel, suggest that life did not originate on Earth, but instead originated elsewhere in the cosmos and propagated through space, perhaps via hardy microbial spores embedded in meteorites or comets, hitchhiking across the interstellar void. While intriguing, and while some organic molecules are found in meteorites, this theory merely shifts the origin question from Earth to another cosmic locale, without solving the fundamental puzzle of how life first arose from non-living components. It simply moves the birthplace. The most widely accepted scientific explanation today is the, quote, biochemical theory of abiogenesis, sometimes referred to as chemical evolution. This theory posits that in Earth's primordial broth or warm little pond, a complex mixture of inorganic molecules in early oceans, subjected to intense energy sources like lightning, volcanic activity, hydrothermal vents at the bottom of the sea, and powerful ultraviolet radiation from the young sun, simple organic molecules naturally formed and accumulated. Under these harsh but energetically rich conditions, these simple building blocks polymerized into more complex macromolecules, eventually leading to the formation of self-replicating molecules, like RNA, which can both store genetic information and act as an enzyme, and rudimentary metabolic pathways. These molecular systems, enclosed within simple lipid membranes that provided a distinct internal environment, would have given rise to the earliest protocells, gradually evolving into the first simple prokaryotic cells, the ancestors of all life. Our early Earth, far from being a tranquil paradise, was an exuberant Earth, a constantly volcanic, geologically active planet, relentlessly bombarded by meteorites and comets, its atmosphere a reactive crucible. This energetic environment provided literally trillions of, quote, biochemical experiments, a vast, natural laboratory for the emergence of life. From this dynamic crucible, the earliest prokaryotic cells, simple, single-celled organisms without a nucleus, like bacteria and archaea, emerged approximately 3.5 to 3.8 billion years ago, as evidenced by ancient stromatolites and microfossils. Over vast eons, these simple life forms evolved, eventually giving rise to more complex eukaryotes, with their specialized organelles and nuclei, and ultimately to multicellular organisms, leading to the breathtaking vast diversity of life we see today, from fungi to redwood trees to human beings. The entire story of life on Earth, when compressed into a single 24-hour cosmic day, reveals intelligence, as embodied by humanity, blossoming only in the last few seconds before midnight, a testament to the immense timescales involved in biological evolution and the incredible patience of cosmic processes. The driving force behind this incredible diversification and adaptation of life is natural selection, a concept of profound elegance and explanatory power, independently discovered by Charles Darwin and Alfred Russel Wallace in the mid-19th century, and inspired by Thomas Malthus's work on population growth and resource scarcity. Natural selection explains evolution. In any population of organisms, individuals with advantageous genetic variations that enhance their survival and reproduction in a challenging environment are more likely to pass on those traits to their offspring. Those less well-suited are less likely to survive and reproduce. Over countless generations, this differential reproductive success leads to the gradual adaptation of species, shaping their forms and functions to their specific ecological niches. It is a blind, non-teleological process, meaning it has no foresight or ultimate goal, simply acting on the variations that arise, constantly striving to catch up with a changing world, selecting for whatever traits happen to be most beneficial in the present moment, a continuous dance between life and its environment, leading to ever-increasing complexity. The emergence of intelligent life, particularly self-aware, language using intelligence like our own, poses unique and profound questions that delve into the realms of neuroscience, psychology, and philosophy. Why did human beings develop such extraordinarily large and complex brains, organs that consume a disproportionate amount of our body's energy and resources? Various theories abound, but one compelling hypothesis suggests that early social groups, facing intense pressures for survival against powerful predators and competing with other hominid groups, selected for enhanced cooperation and communication through speech. The ability to coordinate complex hunts, share intricate information about resources and dangers, plan collaboratively, and transmit accumulated knowledge across generations would have conferred immense survival advantages. Language, in this view, is not just a tool for communication but a powerful shaper of thought itself, enabling abstract reasoning, symbolic representation, cultural transmission, and cumulative knowledge. Characteristics that may be the defining factors that ultimately led to our unique brand of intelligence, allowing us to build civilizations and ponder the cosmos. But what, fundamentally, is life? The scientific method often employs reductionism, viewing life as merely the complex interplay of physical and chemical processes, ultimately reducible to the laws of physics and chemistry. While powerful for understanding biological mechanisms, from molecular biology to genetics, reductionism often struggles to fully explain the subjective experience of life, the phenomenon of consciousness, the feeling of being alive, the qualitative richness of our inner world, the qualia of experience. Conversely, vitalism, an older philosophical concept, posited a non-physical life force, or élan vital, animating living organisms, a spark of something beyond matter. However, vitalism typically violates the containment principle of science, which states that all observed phenomena should, in principle, be explainable by the laws of nature operating within the physical system, without recourse to external, non-physical agents. The subjective experience of life, the qualitative richness of consciousness, remains perhaps the most profound and elusive riddle at the intersection of science and philosophy, a mystery that continues to challenge our deepest understanding of ourselves and our place in the universe. Given the vastness and antiquity of the universe, is life truly unique to Earth? From a purely statistical and cosmological perspective, the probability that Earth is the only planet in the entire cosmos to harbor life, particularly intelligent life, seems incredibly small, almost negligible. The universe is too vast, too old, and contains too many stars and planets for life to be a singular, isolated miracle. Life beyond Earth is therefore a compelling and widely embraced possibility, an idea that has fueled both scientific exploration and popular imagination, inspiring generations of storytellers. As early as the 17th century, Christian Huygens, in his visionary work *The Celestial Worlds Discovered*, eloquently envisioned countless inhabited planets orbiting other suns, each teeming with its own forms of existence, adapting to their unique cosmic environments. The modern search for extraterrestrial intelligence, SETI, actively listening for signals across the vastness of space, is a testament to this enduring curiosity and scientific hope. To quantify this possibility, astronomers and exobiologists use the Drake equation, a probabilistic framework developed by the American astronomer Frank Drake in 1961. This equation attempts to estimate the number of extraterrestrial technological civilizations, ETCs, in our own Milky Way galaxy by multiplying a series of probabilities. The rate of suitable star formation in the galaxy, the fraction of those stars that have planets, the average number of planets capable of supporting life per star, the fraction of those life-capable planets where life actually arises, the fraction of life-bearing planets where intelligent species that develop technology capable of interstellar communication, and finally the average lifetime of such a tech. Optimistic estimates, depending on the assumed values for these probabilities, can yield millions of ETCs in our galaxy alone, painting a vibrant picture of a cosmos teeming with intelligent life. Conversely, more pessimistic, but equally plausible, estimates suggest that we might be alone, or nearly alone, in our galaxy, making our existence all the more precious and, perhaps, all the more fragile. This leads us to the haunting and provocative question known as the Fermi paradox, famously posed by physicist Enrico Fermi in 1950. Where are they? If, even with conservative estimates, the galaxy should contain a significant number of technological civilizations, and if interstellar travel, even at sublight speeds, is theoretically possible over millions of years, then the entire galaxy should have been colonized or explored in a mere fraction of its age. The absence of any observed definitive evidence of ETCs, no signals, no probes, no grand galactic empires, no megastructures, is deeply puzzling, a profound cosmic silence in a universe that should, by many accounts, be humming with life. Various explanations have been proposed for this cosmic silence. Perhaps a galactic selection mechanism is at play. Aggressive civilizations might inevitably self-destruct before achieving interstellar capability, a cosmic filter that prevents widespread expansion beyond their home planet. Or perhaps, more subtly, there exists a galactic club of peaceful, highly advanced civilizations that actively observes us, enforcing a zoo hypothesis, preventing overt contact until we, as a species, prove ourselves worthy, mature enough, or capable of joining the cosmic community without self-destruction or disrupting their own evolution. The paradox remains one of the most compelling and sobering questions facing humanity, forcing us to confront our place in the universe, our potential loneliness, and the possibilities of our own future, a mirror reflecting our own potential and perils. Our revels now are ended. The cloud-capped towers, the gorgeous palaces, the solemn temples, the great globe itself, all that inherit, shall dissolve. We are such stuff as dreams are made on, and our little life is rounded with a sleep. In this vast, enigmatic cosmos, we, the dreamers, continue to weave our universes, finding meaning not in definitive answers, but in the ceaseless, profound act of asking, in the quiet wonder of perpetual inquiry, in the very act of seeking. The gentle hum, weaving beneath these thoughts, now guides us more deeply towards slumber, carrying the echoes of cosmic wisdom into the quiet depths of the subconscious, a comforting journey into the mysteries that define all that is and all that might yet be, waiting for us to discover. Rest well, knowing the universe continues its grand, silent ballet, even as you dream, its secrets patiently waiting for another dawn.